Dr. Bly, by the way.
Should identify myself.
Are we recording? Yes, we're recording. Okay.
Okay. Let's take a. I'm off camera here, so I better come out here.
Here we go. Let's take a quick look at the syllabus, just so we're all on the same page. Down the left-hand side in that blue box is my contact information. So you can find me in my office here, 129. It's 1, 2, 3, 4 doors up, I think, on the right. Except on Wednesday, and I'll be on Greenbrier campus Wednesday. And, just ask anybody where the science lab is, and they'll tell you. It's room 407, so you got to go to the top floor. You get off the elevator, you go to the end of the building. We're at the very end. I guess that's in case we have an explosion and it'll blow out the side of the building. Let's see. If you call my office, I may be there, I may not, but just leave a message. The messages are always converted into audio files and sent to their email addresses. So we get response pretty good. My cell phone's there too. The best way to use my cell phone is a text message. Okay. We only meet once a week for almost 3 hours. The textbook, you need to buy CHEM102 Unlimited. That way, it's the most cost-effective way to get both the electronic textbook and access to the homework. So you have to, we have some homework that's online with CHEM102. And I've got nauseating details in here about how to do that. Oh, by the way, I didn't bring the details. CHEM102 is doing live tutoring sessions for anybody that wants to access those. I'll have to get that information and send it to you. So if you have trouble getting into the website, logging on and doing that type of stuff, then they can help you out. So let me make myself a note of things I need to do. Okay, I'll send that to you on your, and our communication is always through the New River email system. If you have a personal account, I guess you can send me messages if you want from your personal account, but they want us to communicate through the New River email system. Okay, so you need that CHEM102 Unlimited. While we're on the subject, there's no lab manual that you have to buy for the labs. All you have to, and we'll talk about it later, you just need a lab notebook. I give you all the lab handouts in person, and they're on Blackboard. And if I don't say it several times, everything I hand out in class is also available in Blackboard. So if you lose your copy or you're absent one day, you can always get that information in Blackboard. Okay, you're going to need a calculator if you don't already have one. If it says scientific calculator, it'll have all the functions you need. And those, you can use any kind of calculator you want, except during tests. During tests, you have to use a bona fide calculator, no cell phones. I learned that lesson the hard way. Cell phones are too smart. So you can use a calculator and you can also cheat. Let's see. I'm looking for other things. We will, the best thing to do now is to go to the schedule. And actually, the page before the schedule has the grading scheme We're on a 10-point scale. So you get 90%, you got an A. Overall average. There's no final exam. There wasn't time for one. Okay, so don't everybody clap and cheer. Let's see. We have there's a syllabus test in Blackboard. So all you have to do is just click on the link, and it'll take you to the Blackboard test, and it's simple. You just have your syllabus right there and answer questions. And that gives you 1% right there. So I was very generous with that test. The chapter exams are worth 70% of your final grade. And there are 7 of them. So you can spread it out a lot. 20% with the homework. And there are late penalties. I don't know how there'd be a late penalty for exams unless you don't show up and want to make up the exam. So it's 1% per day. If you're in attendance and participating, which is not a problem with just 2 students, you get 9% for that. Okay, so now the schedule. And and this is what I like to stick to, doing these things on these days. And in the left-hand column with all the yellow in it, those are the actual activities that we do. So you've got homework due dates in there, you've got exam schedules, they're highlighted in yellow. On those days, we'll do exams, and then we'll follow up with the next chapter. So you see from the yellow, look to the right, you'll see a new chapter. That's how we handle it. So we got to finish the exam in time to cover that chapter. Then we always have review sessions the week before an exam. So what do we do during the review? Another one of the handouts that I like to give out, which I didn't have time to print, is a review document. And it looks just like a test. And it's got sometimes copious amounts of problems that will probably fry your brain if you try to do them all at once. So you can take it like you do a test, or you can just hopscotch around, whatever you prefer, and work the problems, answer the questions. There's a key that goes with it, a separate key, gives you the answers. And then there's another document called, I call it worked problems. So if you can't figure out how to work a problem, then you go to that work problems and it shows you how I did it. It's in handwriting. By next week, I'll have a copy to show you. But for now, you'll have to go on Blackboard and print out a copy yourself. The reason I do that is because, well, your 2 best friends in chemistry and sciences anyway are curiosity. You're always curious about, if you work a problem or you study something and it doesn't spark at least one other question, then you're not curious. You want to know more. That's your first best friend. Your second best friend is boredom. If you work enough problems and you're so bored working that type of problem that you can't stand it anymore, that means you know it well enough. Move on. So curiosity and boredom are bywords in this class. And I give you plenty of those sample problems. Now what I do is during the review, I take that document and first I get your input. Say if you're having specific problems, you've worked some of these problems and you just still can't wrap your brain around one particular problem, then we'll work it and try to work out the kinks. And then if you don't have any interest, then I'll just sort of hunt and pick and try to do representative type problems that I may think would show up on the exam. And we'll do that for the review session. Okay. So there's your schedule. There's the topics, chapters. And what else? I'm gonna let you read the rest of it. Let's see, this is 102. I don't think I have any bonus projects in 102. I did in 101. If you need to meet with me and you can't make it to campus, then contact me and I'll open my personal Zoom and we can connect by computer. On page 8, under instructor's office hours, that Zoom ID in red, that's my personal ID, my Zoom ID. So all you have to do is be sure that Zoom is on your computer, you have a webcam and a microphone, then we can connect using Zoom and my personal account. In fact, I've got a download link there. So if you don't have Zoom on your computer, you can install it using this link. And then I give you instructions on how to connect. Okay, additional information. This is stuff that we have to put on. In the appendix 1 shows you how to set up your homework account through Cengage. Their homework is called OWL, O-W-L. Sounds like Harry Potter, doesn't it? The OWL exams. But you have to register with the Cengage homework from within Blackboard. So you go to a homework link in Blackboard, any one of them, click on it, and it doesn't recognize you at first, so it takes you through the login process. And if you purchase Cengage Unlimited using your school account email, then you will be your Cengage Unlimited will be linked in the Blackboard. And then all you have to do is just set up your account from within Blackboard, go through the Cengage connection, and the reason we do that is the Blackboard account is linked to your OWL homework. And whenever you complete something in the OWL, Cengage OWL, the results of that homework are automatically sent to the gradebook in Blackboard. If we don't do it that way, then I don't know, unless I go into the account and actually look at everybody's work, I don't know that you've completed it. But it's linked to Blackboard, and I can see it in Blackboard once you've completed the work. Appendix 2. Oh, if you, in fact, if you can't make it to class for some reason, but you're ambulatory at home, say, you can connect to the class through Zoom. You can zoom into the class, and that way I can count you present. Okay, things like that happen. Let me just call up Blackboard and show you. I should have been doing this at the beginning. So, yeah, just show that. Now, is it chopping anything up for us? Yeah, it is. Don't tell Seth what it is. I don't even know how to adjust. Still crooked. Has anything fix that? Okay. That's another thing. Working from home, I'm used to my home computer. And compared to these things, these are dinosaurs. My home computer would just blow them out of the water.
All right. Not now. Okay, so here's Blackboard up here. And you have to log in. Okay, so you find your course. You're going to see a lot of extra stuff here because this is the instructor's screen. Let's see. No, that's not the one. Let's try that again. One or two. All right. Maybe I better use the student view. This is what you'll see. There we go. So start here. There's your, I put the schedule in here also. And there's a syllabus and it's got my schedule in, my personal schedule. Oh, I didn't give you that either. Okay, let me show it to you. So there's my schedule. And it downloads. And then just, try to load it up. There we go. Come on. So this is my schedule document. And I'll eventually print a bunch of these out and leave them sticking in my door. Come on. You get spoiled by my home. I know. There we go. So there's my laser pointer. There you go. So you can tell where I'm supposed to be at all times. Here we are. And then we'll be followed up with the lab. We're just going to talk about the lab a little bit today. And use most of that time to finish up the 2 chapters. Office hours in the afternoon. It's a good idea if you want to see me during office hours to give me a ring. See if I'm there. Other responsibilities might take me away. So that's the only time we're going to meet. The other times, you got office hours here, here, and here. I'm off campus here. So you'll not find me in this vicinity on Fridays. Unless you want to come to Logan. I don't know too many people who do want to come to Logan. Okay. So you can print out a copy of that out of Blackboard. And let's go back. Okay. So let's see. If you don't have a PDF reader, these are a couple of good ones. Like this link. Foxbit's a good one. Adobe Acrobat actually produces a free reader. And here's your CHEM102 homework link. This is the one, I put this one on the main page so that you wouldn't have trouble finding it the first time through. And you just click that and it'll take you to the CHEM website where you log in and register. But when you go to do homework for each chapter, go down to this homework link here. And then each one of these individually, once you're registered, it'll take you straight to that chapter homework. Okay? And once you have registered, you can go to this link will take you to the textbook, the electronic textbook. If you want a hard copy, you can buy a used version for little or nothing, or you can request a loaner from CHEM, and they'll send it to you for about $8. You can keep it for the semester. I like to have a permanent hard copy that I keep in my own library. I mean, I've always been that way. It's just personal preference. So I've got more books than I've got room for. Most of them are still in boxes. Okay. Let's see. This folder is all the lectures and all the reviews that we're going to do. I'll come back to that in a second. Let's see. These are solutions to the end of the chapter problems in the 9th edition. So I'm not sure how the numbering will go in later editions. But these give you solutions for every problem. They're not as detailed as the document that I prepared for you, for problems. But I put that in there for people who want to do it. Let's see. Here's your knowledge test, the syllabus knowledge test. Just click on that. It takes you to a Blackboard test, and then you just begin. It's not going to cut you off on a time limit. You just go in, answer the questions, and submit it, and you're done. Okay, so let's look at this for just a second. Lectures and reviews. So you can see how it's organized. It's organized by exams, actually. This first one is chapters 10 and 11. So here you're going to see chapter 10 will have the PowerPoints here. And they come in 3 flavors. These are the PowerPoint slides here. This is a PDF file that I created from the slides in case you don't have access to PowerPoint so you can view the slides. And then this one is one of my favorites. This one is an HTML conversion of the PowerPoints. So within your browser, you don't need PowerPoint. Just click on this thing, and it comes up in your browser. And you can scroll through the slides. Yes. It even includes animations if there are any, or videos. I used to have a free version that worked, but it quit working when I went to Windows 10. So I had to shell out some money to get one that worked, which was worth it. Okay, let's see. All right. So that's and chapter 11 is the same. Down here are videos. These are web links to YouTube. I post all my videos on YouTube. So you click on these, and you see that these say previous semester. Those are old videos. If you go back, the oldest one's probably not very good quality. But if you get one that's recent, like here, this one in January for chapter 10, this one in January for chapter in February, and then reviews, then you can see those sessions. If you can't wait until I post our sessions here, You can go ahead and view those. Might gain a different perspective on what we covered in class. Then you have the review folder underneath the chapter folder. Here's where you get the review document. This is a PDF form. And then here's the key. And it looks exactly like the exams I hand out in class. So there are no surprises when you walk in with the exam. It looks exactly like this thing. And here's the review work problems. This one right here, this chapter 11 review, that's within Blackboard. If you want to drill your knowledge in Blackboard and it'll grade you, and then you can go back and take it again, it's grading you, but I don't see those grades. They're for your benefit only. It'll take you through a Blackboard review of that chapter. Okay, so this is what the review document, work problems looks like. Let's see if I can look at it in the system. Here we go. So there you see, I try to write as legibly as possible. So there are your problem numbers. Sometimes the numbers are in sequence from front all the way to the end. Sometimes they're grouped. So you have to pay close attention. Now this is not the only way that you can work a problem that I show you here. This is the way I worked it on that day. And actually in class, if we work the same problems, I might work them a little differently. All right, any questions so far? Probably spend enough time on this. Okay. Close that, get back to our PowerPoints, and then we'll look at, start with chapter 10. And start a slideshow. If you need to take a break, just pop up and go. You don't have to ask permission. I'll just keep talking. If you miss something important, it's recorded anyway. All right. Let's see, did I miss anything on the... No, I think we covered everything in the syllabus. So I'll stick it back in here. And this slides. I'll have to move through pretty quickly to get it done today. All right. Chapter 10. Liquids and solids. We know, we have a general idea of what liquids and solids are. Liquids, they have definite volume, but they don't have a definite shape. And solids have a definite shape and volume. We're going to investigate why that is, not just classify things as liquids and solids. It's like, why is a liquid and not a solid? Or when does a liquid become a solid? And why does it become a solid? Okay. We have to think about the forces that are holding molecules together. All molecules, and all atoms for that matter, that are in close proximity to one another are either attracted or repelled to one another. Now we have to distinguish between the types of bonds, and we do that in two categories. One is intramolecular bonding, which is, those are the bonds that hold molecules together. Okay? They're usually very strong. Otherwise, the molecule would not retain its integrity under extreme conditions. And molecules, we're going to restrict our definition here to those
collections of atoms that bond by sharing electrons. Those are covalent bonds. We covered that in the first, I think we did, at the end of the first 101. Yeah. I'm scratching my head. We covered covalent bonds. And that's what molecules do. They are very strongly bound with covalent bonds. So they also interact with one another with intermolecular forces. And these forces can occur in different forms based upon their strength of attraction. And we'll define these in more detail in a few minutes. There can be dipole forces. In other words, if a molecule is polar, in other words, it's slightly negative on one side and slightly positive on the other, it's not a full charge, just a slight charge. And that slight varies also. Then those molecules will yeah. Here it is. Those molecules will, just if a molecule is like this and it has a slight positive charge on that side and a slight negative on that side, that little delta sign means slight. It's not a full charge. Then the molecules will line up with one another like that. Those are dipole-dipole interactions. It's an electrostatic attraction. Positive attracts negative. And there are gradations of the strength of this bonding. And the strongest of those bondings are hydrogen bonds. Let me see that I don't get ahead of myself. Yeah, we're going to talk about hydrogen bonds on another slide. Then the forces get progressively weaker, especially for molecules that are non-polar. In other words, they don't have this uneven distribution like that. You can think of them as blobs. I mean, they don't have any permanent distribution of charge. So how do you get them to attract one another? They do attract. We know they attract because, for instance, there's nitrogen, dinitrogen in the atmosphere. It's a gas right now. But if you cool it down and compress it, it'll eventually turn to a liquid. Well, that begs the question, why do things become a liquid when they would rather be a gas? Well, there has to be some attraction between this nitrogen molecule and this nitrogen molecule in order to form a liquid. Okay. So the way they do that is with London dispersion forces. And we'll define those also in just a second. One overriding concept is that intramolecular bonds, those that hold molecules together, are always stronger than intermolecular bonds that attract molecules to one another. I mean, logically, if the intermolecular forces exceeded the strength of the intramolecular forces, it would rip the molecule apart. So this has to be. It can't be any other way. All right. So this is an example of hydrogen bonding. And as the name implies, there's always a hydrogen involved. The hydrogen is bound to an electronegative atom, like oxygen, fluorine, nitrogen are the most common ones. And the reason for that strength of bonding is that hydrogen has just got one electron, and it's not very electronegative.
And these highly electronegative atoms draw electron density away from the hydrogen, which gives it a slight positive charge. So for the oxygen-hydrogen bond in water, you get a dipole in this direction. Right? For the oxygen, this means positive side, this is the negative side. So you get a slight negative here, and you get a slight positive on those. So when they, in pure water, they orient themselves oxygen to hydrogen. And those dipole-dipole interactions are the strongest of all the dipoles. That's why water is a liquid at 1 atmosphere pressure and normal temperature, room temperature. If it weren't for this dipole-dipole interaction, this hydrogen bonding, water would be a gas, and we'd all be in big trouble. There wouldn't be any liquid or solid water on the surface of the earth. Okay, this is just a review. Intramolecular bonds are always stronger than intermoleculars. And this is just in words what I was telling you earlier. Now these slides, like I said, they're all on Blackboard. So you can just jot down periodic notes if you want. You don't have to copy down everything that's up here. And that's why I like to hand out copies, hard copies of these slides, so that you can jot things in the margin. You don't have to write everything down. When I was a student years ago, we didn't know anything about this stuff, right? You had a notebook and a pen, and you wrote furiously to get everything down. And then sometimes, remember one course, I had a tape recorder. And I recorded the lectures, and then I went home and recopied my notes. And you miss half of what goes on in class. That's just a fact. In fact, this teacher was so nice. If I were just a couple of minutes late, he wouldn't start the class until I came, sat down, and hooked up my recorder. Okay, so these phase changes between solid, liquid, gas owe their existence to intermolecular forces, what's holding them together. So those changes in state owe their existence to the forces between molecules. But there's a link between the intermolecular forces and the intramolecular forces, because the intramolecular forces determine what type of electric charge there might be on the molecule. So they're related. So this is sort of a general. Solids, of course, have a regular structure, and they're close together, and they have strong enough bonds that they can maintain their own volume and shape. Liquids are a little farther apart. The intermolecular forces are a little weaker, so they slide past one another. That's why they can't maintain their own shape. Gases, by comparison, they're just miles apart, and they're flying at enormous speeds. One calculation we did in class, these molecules were moving faster than the speed of sound. That was between strikes. They move really fast, and then they smack into somebody else, go off in another direction. But the distance between them, compared to the size of the molecule, is massive. There's lots of space in gases. That's why when you put two gases together, you always get a solution. There's perfect mixture no matter what the gases are. There's no heterogeneity about gas mixtures. They're always homogeneous because there's plenty of space. Okay, oops. Okay, so what happens during a phase change? If we go from solid to liquid, solid to liquid to gas. And I'll use, when we write our balanced equations, we use these identifiers. Remember that? When we say water is in a reaction as a liquid. So that's what I'm using here. So as energy is added to a solid, you start to get vibration. Right? The molecules are locked in place, but they can still vibrate. And that added energy makes them vibrate even stronger. And that vibration, that added energy, eventually starts breaking bonds. So once they've achieved enough movement, then they start to become disordered. And that's when they move to liquid. And you see a phase change. And that usually occurs at a definite temperature. Right? Remember what temperature is. It's the average kinetic energy of the molecules. So as the temperature increases, the kinetic energy of the molecules increases proportionally. And once you get enough energy, you can break those bonds that are holding the solid together and make a liquid. Okay? So you keep adding energy. Just keep heating it up or using whatever form of energy works. Sometimes you can use ultraviolet radiation. You can use microwaves, like in our microwave ovens. So microwave energy comes in, let's say, it's usually tuned to a resonant frequency for water. So the microwaves come in like this, and they agitate the water. And then the water starts moving around and it transfers its energy to the food around it. But eventually, you can add enough energy where you can break the bonds of the liquid. And when you do that, then the molecules of a gas are like independent agents. Gases can be treated, ideal gases can be treated as if the molecules don't exist. Right? They're point sources. Now we know that they're the interactions, right? We just showed it with nitrogen. You can cool nitrogen down to a liquid. You just got to get it to minus 195 degrees Celsius. And you can make a liquid out of it. But you've got to get it really cold. Think about it. You have to make it cold because the forces holding the nitrogen molecules together in the liquid are very weak. So it doesn't take much energy to break it and make a gas. So they have to be very cold to minimize this extra kinetic energy that would tear them apart. And that's a basic concept in how phases change. What temperature do you need to maintain depends on the forces that are involved. With dipole-dipole interactions, you need high temperatures, relatively high temperatures to break those bonds. But with weaker forces holding molecules together, it doesn't take much energy. So they have to be really cold. Dry ice, right? A solid carbon dioxide is at a temperature of minus 78.5 degrees Celsius. It's a little warmer than nitrogen liquid because the forces holding it together are stronger. All right. So what happens to density? Well, as a general rule, when you go from solid to liquid to gas, the density decreases. Right? Think about it. If you had the same mass with each one, but you change the volume, then you're changing the density calculation. Right? Density is mass divided by volume. So if this is constant, as you increase this, that has to go down. So you go from solid to liquid, and there's slight increase in volume, not much. But when you go from liquid to gas, you have a massive increase in volume. So the density goes way down. Now, water's a bad choice here for this relationship because water, it sort of defies the trend.
And I'll explain why in just a second.
But typically speaking, when you go from solid to liquid, the density decreases. But from ice to liquid water, the density increases. But this is true. When it goes from liquid to gas, look, the density goes way, way down. It's like 4 orders of magnitude difference. So why does water do that? Let's see if I have a slide over here. So I don't have to draw it. No, I don't have to draw it. So why does water decrease density when it turns to a solid? That defies logic. What happens is, when you go from a liquid to a solid, you develop some sort of, it's not always a crystal lattice, but it's a more regular arrangement of molecules. But in ice, the arrangement is very regular, and you can see it in snowflakes, like 6 points. So you get water molecules arranged in a hexagon with the oxygens here. And then you have a hydrogen sticking out here with its hydrogen bond. Right? Then you have another one out here like that. So this one would have a hydrogen here and then a hydrogen bond there. So they form this regular arrangement, hexagonal arrangement. Well, what does that mean? Look at all that empty space. So they expand in space as a solid. That's why ice floats in liquid water, because it's less dense. And it's a good thing, too. If water followed the trend, there's so much of it on the Earth. If water followed the trend of decreasing density left to right, then what would happen in the winter? Surface of the lakes and oceans would freeze, and the ice would sink to the bottom and be permanently insulated. It'd stay solid, and it would just keep doing that winter after winter until eventually all the oceans and lakes would be solid ice, never thaw. We'd be in big trouble then. And that's why the fish in the winter, they go deep, because it's warmer down there. Okay, let's look at dipoles now. I explained a little bit about dipoles. Each molecule has the potential for polar bonds. That doesn't mean they always do, but every bond has the potential for polarity. In other words, if you get two atoms linked together, the only way that it's purely non-polar is if this atom is exactly the same element as this atom, like nitrogen. Nitrogen here, nitrogen here. Then there's no differential pull on electrons. But if you get something like this, then oxygen is more electronegative than hydrogen, and there's a dipole moment toward oxygen, which gives you a slightly negative charge. So that bond is said to be polar, and we designate it with this symbol. Now, this is for individual bonds. So this bond would also have a dipole moment. But for whole molecules, how do we characterize the molecule? Well, you have to do what's called vector summation. If you've had, well, I don't know. I guess you have to have some physics to understand vectors. In physics, we use vectors to designate the strength of a force and the direction of a force. So if you have something here and you're pulling on it this way with a force, and you're pulling on it this way with a force, well, they cancel each other out if they're equal, right? So if they're equal, this actually would be the summation, the vector sum of this one would be maybe about that much in this direction. We sum them together. Right? This is positive, that's negative. Add them together, you get that much net force. Well, if they're not pulling in opposite directions, if they're off like that, right? How do you do that? Well, a qualitative assessment would be the component that's pulling. You can subdivide this into two components, going that direction and that direction. This one also. So you add them together, and that's what we call the vector sum of those forces. So you see that for water molecules. So which way would the dipole moment be for this one? Well, if we use this symbol here, it would be in that direction for the whole molecule. Because there's this one going that way, and this one going that way, so they add up in that direction. That's a vector sum of our dipole moment for the whole molecule. Okay, so you have to consider two things when you're talking about the polarity of a molecule. First, are the bonds polar? In this case, yeah, both of those bonds are polar, right? Then how do they interact to make, what's the geometry of the molecule to make that polarity of the polar? If they're like carbon dioxide, right? You got this one equal to this one, they cancel each other out. So this one is nonpolar. Even though the bonds are polar, the molecule is nonpolar because the vector sum cancels out. Okay, so these dipole-dipole forces are, on average, only about 1% as strong as covalent and ionic bonds. But they're still significant, especially when you have billions and billions of them in a beaker of water, say. The hydrogen bond is just a special case of the dipole-dipole, and I've explained that to you. It usually occurs when you have highly electronegative atoms attached to a hydrogen. So there has to be a hydrogen plus one of these atoms. There's some argument also that sulfur might also give you some hydrogen bonding, but that's an argument for another time. All right. So what are these weaker forces for nonpolar molecules? The London dispersion forces are due not to permanent dipoles, but to instantaneous dipoles. In other words, electrons are not static. They don't just sit there. They're always on the move. And they tend to flip back and forth in molecules. And when they do that, they produce an instantaneous redistribution of charge. So let's take a long chain aliphatic compound, like, let's see which one. 1, 2, 3, 4, 5, 6. Hexane. So each one of these that I'm drawing there, those are hydrogens. I'm not going to drop H's in because they clutter things up. But for this hexane, at room temperature, it is a liquid. I mean, it's a very volatile liquid. I mean, if you open the container, you can smell it. But it's still a liquid at room temperature. So there have to be some forces involved holding those hexane molecules together in the liquid state. So what are they? Well, if you have two hexanes side by side,
like that, say one of them experiences an instantaneous redistribution of electron density. So this end of the molecule becomes slightly negative and this end becomes slightly positive. Just for a microsecond. That's all it takes. When it does that, in the molecule that it's close to, it induces an attraction for electrons. Well, this is repulsion. This is attraction for electrons. So it shifts the electron density this way by that attraction. So this end becomes that, and this end becomes slightly depleted in electron density. So what do you have now? For that microsecond, you have positive against negative attracting, negative against positive attracting. And this can happen all up and down the length of that molecule. So that's a London dispersion forces. We're dispersing the charge temporarily, long enough to get that attraction. Now, these forces are very weak. So it's easy to break those bonds. It's more significant in large molecules, right? Because you have more electron density here, scattered about, and it's in higher flux. So the larger the molecule, the stronger the London dispersions. And you can see that as a trend in hydrocarbons, right? We have the hydrocarbon homologous series, 2, 3, 4, 5, 6. Let's just keep going. Go down to octane. And each of these has hydrogens on it. Right? So this would be 6, this would be 8, this would be 10, this would be 12, this would be 14, this would be 16, and this would be 18. So those long molecules, and you find that the melting point, actually the boiling point, I say the boiling point for these is increasing this direction. So the longer the molecule, the more opportunity you have for these redistributions to occur and lined up with these parallel molecules. So you get an increase in boiling point as the molecule gets bigger. So when you get to diesel fuel and asphalt, asphalt turns into a solid, actually, because of these forces. Okay. London dispersion forces are always there, even in polar molecules. But if there is a true dipole-dipole interaction, they're so much stronger that the London dispersions don't matter. They're just too weak. They're only significant when there are no competing dipoles. Okay. So in general, the stronger the intermolecular forces, the higher the boiling point and the higher the melting point. That's just a general trend, and it follows from the descriptions that we've given. So this comes straight out of your book. So if we focus on the second period, this one right here, lithium, beryllium, boron, on across to neon. Let's see. Where am I? What's carbon, nitrogen, fluorine? Yeah, okay, here we go. These are, we try to, when we put these homologous series together, we try to only, we leave one variable out. Everything else is uniform. So these are all hydrides. There's hydrogen, 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 hydrogen. The only thing that changes is this atom here. So what happens to the boiling point? Well, if we go from here to here to here to here, we would assume that as the boiling point increases, you should get an increase in intermolecular forces. You do. Right. So the carbon should be the least electronegative of all these atoms. Nitrogen is a little less electronegative. Fluorine is less electronegative than oxygen. Actually, that's not true. It should be flipped, because fluorine is the most electronegative atom on the periodic table. But there are other, we have to explain that anomaly. And that's beyond the scope of this chapter review. We look at it the other direction. Right? If you go groups up and down, that's what left to right is groups. So if you go, there's tellurium, selenium, sulfur, and then what should be down here? Oxygen. So here, tellurium, selenium, sulfur, oxygen. If you follow the trend, then water should be down here. Right? It goes like that, trend there. This one goes down here, right? Nitrogen should be down here, but it's up there. And fluorine should be down here, but it's up here. The explanation for that, all of these, now carbon behaves. Right? Why? Because carbon is methane, CH4, is nonpolar. It has no dipole interaction. None of these do. So they're all London dispersion force attractors. But when you get down to here, the reason that all of these are higher than they were expected to be is hydrogen bonding. Here, here, here. That dipole-dipole interaction. These molecules here are not electronegative enough to induce dipole, hydrogen bonding. Now they may have dipoles, but they're not nearly as strong as the hydrogen bond. So that's what this anomaly is all about. So which one of these are capable of forming stronger intermolecular forces? You have to know something about the bonds and the geometry. And based upon what we've looked at so far, this would have these stronger intermolecular forces because it's hydrogen bonding. And nitrogen is nonpolar. And there's your explanation. It's the type of force that we use to bind them together. Hydrogen bonding versus London dispersion forces. So very weak. Now this illustrates structure. Right? Geometry has an influence on the intermolecular forces. Right? These molecules have exactly the same formulas. Right? Two carbons, one oxygen, 6 hydrogen, 6 hydrogens. This one's arranged differently. This oxygen here is bound to carbon, whereas this oxygen is bound to a hydrogen. So you have hydrogen bonding available here. This is ethanol bonding, the drinking kind. And this is dimethyl ether. Right? So you get this structure which is balanced on both sides. So any dipoles that would form in here are canceled out. But here you have one on that end. So this one is going to have a higher boiling point. Okay. I didn't have an animation on this one. So what do we mean by behaving more ideally? If you remember from the first semester, chemistry, ideal gases, gases behave ideally when they what? When they don't interact with one another. The molecules do not interact. They behave like point sources. And they just bounce off each other. There are no intermolecular interactions. So when does that happen? In a gas, it happens
at high temperature and low pressure. High temperature means they have lots of kinetic energy, right? So their interactions are overwhelmed by the force of impact. Low pressure means there's not many molecules in there, right? So they don't interact that much anyway. So this one is going to behave more ideally simply because the only forces available to it are the weakest ones, the London dispersions. Whereas carbon monoxide does have the ability to form dipole. Because so there's an uneven distribution. This is more electronegative than carbon, so you're going to get a slight dipole in this direction. Since there are only two atoms there, it's linear. There's only the whole molecule behaves according to that bond polarity. And there's a discussion. So what else do we know about liquids? Well, they have low compressibility. They're not incompressible. We know that because samples have been taken of waters at very deep, 2 miles, 3 miles down in the ocean, and the density of water is measured by remote devices down there. And they find that the density of water at that depth is measurably greater than it is on the surface. So liquids are compressible. They don't compress easily. They're not rigid. They don't hold their own shape. And they have generally high density as compared to gases. They exhibit a phenomenon called surface tension. And this is, in simplest terms, it's a resistance of the liquid to increase its surface area. In other words, it wants to minimize surface area. Some liquids have higher surface tension than others. Water's got a very high surface tension, and it's related to the intermolecular forces. The stronger the intermolecular forces, the greater the surface tension. Have you ever seen pictures of, or film of water skimmers? Little bugs that ride across the surface of the water. You'll notice that where their feet touch the water, there's a depression. They're taking advantage of surface tension on the surface of water. It's difficult for them to do it in agitated water. They have to do it on calm water. Or I did this as a kid once. Take a needle, very gently lay it on top of water. If you're lucky, it'll sit right there. The surface tension is strong enough for water to hold that needle up. Okay, other things that are characteristic of liquids that can be related to these intermolecular forces. Capillary action. Capillary action is spontaneous rising of liquid in a narrow tube. And it's easy to demonstrate. Either in the lab with a piece of capillary tubing, you can watch it. Or you can demonstrate it in with living systems. Take a reed or a stalk from a plant, cut off on both ends, stick it in water, and it will eventually, water will come out the top. It may not come very fast, but the capillaries inside that stem are small enough. So what's happening? Well, there's a competition between adhesive and cohesive forces. Right? So if the level of the liquid here, right, starts here, well, what's going on? You got two types of forces. One holding these molecules together, pulling, and then those are cohesive forces. Adhesive forces between the liquid and the surface of the tube. So if there are cohesive forces strong enough between the tube and the liquid, then they tend to pull that liquid up like this, like attract it to the surface of the tube. For instance, water in a glass tube. Well, what then happens? Well, as they move up like that, you still got the cohesive forces, and they tend to pull the water up to balance. And they keep doing that until the mass of water, in this case, here, matches the force that's holding them up, the adhesive forces. So that's why the narrower the tube, the higher it goes, right? Because there's sufficient force to hold up a certain mass. And if the tube is narrow, then you know how the volume of liquid in a narrow tube is longer. The volume of a cylinder, right, is height times area. So if you decrease the area, then the height has to get bigger. So the capillary, the narrow tube, will make it go higher. And this is a phenomenon simply because glass tubing is a borosilicate mixture. And silica has these oxygens and hydrogens sticking out on the surface. So there's opportunity, particularly for water, to form those adhesive bonds. Now, when you get mercury, it goes just the opposite. It forms a convex because it's not attracted to the glass. The adhesive forces are greater than the cohesive forces. So the meniscus in a glass tube of mercury is like that. Whereas with water, it's just the other way around. Okay. Well, there you are. I explained it. There's a picture. So if you've ever seen a mercury barometer, I don't know if you have, they're kind of rare. They measure air pressure, the column of mercury. You take your measurement at the top of the meniscus right here. With water, remember, in our glassware, it's calibrated to measure at the bottom of the meniscus. So cohesive forces here win for mercury. But with water, the adhesive forces are stronger. Okay, another characteristic of liquids is viscosity. So what is viscosity? Well, we can think of it in practical terms, right? It's like molasses in winter. It's very high viscosity. As it gets colder, it doesn't flow very well. In fact, you can leave a bottle of molasses outside in the winter, go out there and pick it up. Nothing comes out. But the more viscous a liquid, the more strongly it resists flow. In order to flow, remember, the molecules have to move past one another. They have to be able to slide. And if the intermolecular forces are stronger, then they don't slide as easy, and the liquid is more viscous. Oops. There we go. Okay, solids can be subdivided into two groups based upon their structure. They're either crystalline, which has a very ordered, regular structure, and amorphous liquids that have a disordered structure. But they're still, molecules are locked in place, but they're disordered. Glass is an example of that. In fact, there's one school of thought that says glass ought to be considered a supercooled liquid. It's It's neither here nor there, I guess. But they're amorphous. Whereas crystalline solids are like table salt. If I spill salt on the counter, I got to pull out my magnifying glass and look at it. It's little cubes. And that gives you an indication what is the internal structure of salt. It's cube-shaped. Okay. There are a number of ways to describe crystalline solids. This is one way. The unit cell. This is the smallest three-dimensional repeating unit in a crystal. So once you've identified what the unit cell is, you can repeat that infinitely in all three dimensions. And you still have the same structure. That's one way to describe it. The second way is by the closest packing structure. And this is derived from the assumption that when solids in crystal form pack together, they minimize as much as possible both their energy and their physical distribution in the crystal. So they want to pack as close as possible. Think of marbles. When you see marbles in a glass container, where do the marbles in each layer sit? They sit in the depressions, right? They minimize the amount of free space. This is the closest packing structure. Okay, unit cells. There are a host of unit cells that can be described for a crystalline solid. These are the three most common. And that's not very large. I mean, it comes straight out of your book. There's the simple cubic. So you have at the edges of the cubes, you have 8 atoms. We just, for simplicity's sake, we're just going to say atoms here. And actually, to make it simpler, metal atoms form a simple cube. This is one way, the ball and stick model. This is allowed us to expand this cube into more cubes put together. And this is instructive because you notice that when you take this simple structure and repeat it, that one right there belongs to how many? Well, let's look at this one right here. How many other cubes does this one belong to? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. That one right there is only 1/8 belongs to this cube. See what I'm getting at? And this is a space filling model. This is actually what it would look like. So they're touching. These corner atoms are touching right here, here. With the next one, where you have a body-centered cube, you have one in the center of a cube. They don't touch because that one in the center is pushing these others apart. Okay, that's important when you start to do calculations, to recognize that. And then you look at this cubic structure. So how many atoms belong to that cube? Well, that one in the center belongs wholly to that cube. That whole atom stays there in that cube for your calculations. There's one atom there. But each one of these belongs to 8 others, or 7 others. So it's only 1/8. So 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1/8 is 1. So if you're calculating how many atoms belong to that unit cell, 1 here, and then 1 from the corners. But here, you've only got 1 atom per unit cell because it only lays claim to an 1/8 of each one. Okay, see where I'm headed with this? I hope. The face-centered cube takes an atom and puts it on the face of the cube. Nothing in the center. It's all on the face.
So you got these corners, an 8 of them, so that's 1 for the corners. How many on the face belongs to that cube? A half, right? Because it can only interface with 1 cube on its face side. So half of it goes here, half of it goes there to the other cube. So how many do you have? 1, 2, 3, 4, 5, 6. 6 atoms on the faces of a cube. That means you have 3 total atoms per unit cell, because it can only lay claim to half of 1 on each face. So 3 plus 1 is 4. So if you look at it, this one has 1 atom per unit cell, this one has 2, and this one has, what did I say, 4? Yeah. 4 for the face center cube. Now it helps if you're a visual spatial learner to see this stuff. It's difficult for me because I'm mostly left brain. It's all numbers and calculations for me. So it takes a lot of work for me to see this. But some students just pick it up like that. That's the way they learn. And as a general rule, not to be prejudiced or sexist, but women tend to do better with these spatial things than men do. Because women are more right brain than men are more left brain, as a general rule. Okay. So here's how we gain information on the structure of regular crystalline solids. We use this equation. Now, what does that equation mean? Well, it's given the name of the inventor, the Bragg equation. And in order to use it, you need an instrument that will fire X-rays at a crystal. I used one of these when I was doing research on soils, because the clay fraction in the soil is very regular structure, and you can get it plated out on a slide, just like a microscope slide, stick it in this machine, and it fires X-rays at it. And then it measures the energy bouncing off of it. The energy is going to be maximum at a certain angle. That's this angle, theta. And this, D, is the distance between the atoms in the layers. So you've got layers here of atoms. Even though you've got your crystal structure, it forms into regular layers. So when the light comes in like this, some of it bounces off the surface, some of it bounces off inside, right? And I think we talked about first semester interference. We talked about interference. If you have a wave like this and a wave like this, right, and combine them, right? The humps match the troughs, so the combination is positive interference. Negative interference would be if they're shifted, and then one would cancel the other one out, or partially cancel out. So that's what we're looking for here. I forgot to silence my phone. One second. I got a little ad. Called silent time. Just turn it on. During this time slot, it will let it ring. So you get a reflection here and a reflection from inside the crystal. And then they positively or negatively interfere with one another. If they positively interfere, then you get your detector out here that picks up the signal, and it forms at different angles. This is the angle of attack. Then you get a maximum here. This is intensity. So that maximum tells you what angle is maximum intensity, And you can relate that angle to the distance between the layers based upon the wavelength of the X-ray and this integer. Okay, so that's the Bragg equation. Oh, instead of drawing it, I should have just flipped to the next slide, right? This is a test to see if I know what I'm talking about. So, this distance would be related to the unit cell. Right? So the distance between those layers in the unit cell, depending on where the atoms are located, could be ascertained by this method. And there are several problems in the review document attacking this particular problem. Okay. Now, that is a two-dimensional, actually a one-dimensional look at the Bragg equation. But if you really want to know something about the structure of a crystal, you need some way to attack the three dimensions of it. And this is X-ray diffraction. Right? So you use the same X-rays, and you pass them through or you bounce them off a crystal. And it gives you this diffraction pattern. Right? And the key here is that this is a regular crystalline solid. That's the prerequisite. It has to be that. So when Watson and Crick, well, actually their female assistant didn't work, we're investigating DNA. The real trick was trying to get DNA into a regular crystalline structure. Once they mastered that, then they could use X-ray diffraction to piece together the double helix basic structure of the DNA molecule. I can't remember the lady's name that did this work, but she never got credit for it, at least not officially. Watson and Crick got the Nobel Prize. I think by that time she was dead, cancer or something. But those were the days. Okay. Types of crystalline solids. We can subdivide them into three basic types. Ionic solids, where you have a positive ion and a negative ion in this crystal lattice. And that's what you would see with salt. You would see sodium ions surrounded by chloride ions. Right? And these chlorides would be surrounded by sodiums. You have to think in three dimensions, right? There are chlorides out here and chlorides in there, which gives you a simple cubic unit cell. Then they're molecular solids. And each one of these points of the lattice, the crystal lattice, is occupied by a molecule, a covalently bound molecule. And that molecular solid, a good example would be ice. Forms that regular hexagonal shape, and that hexagonal shape is like the unit cell. Right? The hexagon goes all directions. And then there are atomic solids, where you have atoms, and the usual example that's thrown out is metals. They tend to behave more regularly than some of these others. It's difficult to get these nitrogen, oxygen, chlorine into an atomic solid because they're gases at room temperature. So we use metals. Metals tend to work better for theoretical purposes. Right, here are examples. Right, everybody knows that. Girl's best friend. This is a this is a covalently bound crystalline solid with atoms. carbon atoms here, each one bound to 4 others. And actually, if you have a flawless diamond, and you were small enough, you could walk one atom to the next, all the way across from one side to the other, and never have to jump. It's one single molecule, covalently bound molecule. And for that reason, it's the hardest naturally occurring substance on Earth. Now, we've manufactured some harder things in the lab. This is the hardest naturally occurring substance that's been identified. And on the Mohs scale, it's got a 10, the hardest. And number 1 on the Mohs scale is talc. It's the softest. Okay, how about this one? Sodium chloride. There's your regular cubic unit cell. Only in this cubic, one of these corners here is sodium, and this is chlorine. Sodium and chloride ion. Sodium here, chloride. So the size of those ions influences the size of the crystal. And then this one is ice. Right, that's an ionic solid. And this one is due to hydrogen bonding. Okay. So this sort of tries to organize things. This part of the chapter is difficult to comprehend. It's even more difficult to teach. Because really to understand this stuff, it's like you've got to get a graduate degree. Right? So we're just scratching the surface, so to speak. Trying to understand it in terms of this intermolecular force discussion that we've had so far. So atomic solids can either be metallic, or you have metal atoms. Again, atomic solids, molecular solids, and ionic solids. That was the 3 main categories. And then within the atomic solids, you can have metallic, you have metal atoms, network, where the diamond is an atomic solid, but they're covalently bound. Here you have a class of bond that we haven't discussed. It's the metallic bond. And then these group 8A, these guys right here, noble gases. When they form solids, they're bound together only by London dispersion forces. So you can have London dispersions in a single atom. That's how we know. In fact, that's one of the main clues for London dispersion, because you can get liquids out of these. And actually, you can form solids eventually. The only way that they can bind themselves together is if there are intermolecular forces there. And London dispersion is the only explanation for that. Molecular solids, where you have discrete molecules. You can have either dipoles or you can have London dispersion forces. And the defining characteristic is that at each point of the lattice is a molecule, not an atom. And then for the ionic solids, obviously have ions instead of atoms. Okay. So we talked about the unit cell. Now let's go to closest packing as an explanation. Unit cell is one way to look at it. Closest packing is another way to look at it. This assumes, and we're going to simplify it. We're going to talk about metal atoms only, just to keep things simple. The metal atoms are uniform in shape, and they act like hard spheres. And these spheres are packed in layers. So what do those layers look like? Oh. Got a video? Yeah, hope it sounds good. No. Here we go.
Hope you can hear it over the fan. Tune into an Indian accent.
Constituent particles in crystal may be thought of as solid spheres. In this video, we should try to understand the close pattern of spheres in 3D space using minimal weighted space. Packing in one dimension. There is only one possible linear one-dimensional arrangement possible in spheres. The keyword linear, each sphere touching the adjacent spheres like this. Packing in two dimensions. To arrange spheres in two dimensions, we take the linear one-dimensional arrangement that was shown previously. There are two ways by which we may arrange the spheres in a two-dimensional platform. They may be arranged like this. Note that each linear arrangement are aligned vertically. Here, the vacant space is this. Now, in this packing, the spheres take up only 52.48% of their available space. Here, a single sphere touches four other spheres. If we join the centers of the spheres, we get a square. Therefore, this packing is called square close packing. The second way of arranging the linear one-dimensional arrangements is to keep the spheres of the second linear one-dimensional arrangement in the depressions of the first, like this. Here, every alternate linear arrangement has the same alignment. These are the vacant spaces, which is visibly less than the square close packing and hence more efficiently packed. In this packing, the spheres occupy 60.4% of the available space. The voids created in this packing touches three spheres forming an equilateral triangle and are called triangular points. A single sphere touches six other spheres. By joining the centers of these spheres, we get a hexagon. Therefore, this packing is called hexagonal close packing. Packing in three dimensions. Taking square close pack two-dimensional layers. This is done by placing a two-dimensional layer just above the first layer and so on. All the layers are vertically aligned. Taking hexagonal close packing two-dimensional layer. The first layer contains red-colored spheres indicating the alignment of the layer. This alignment is called A. These are the void spaces of the layer. We have to place a layer on top of this layer. For efficient packing, we will have to place the second layer in such a way that the spheres are exactly over the triangular voids of the first layer. Only these triangular voids can be covered. So spheres of the second layer are blue in color, which indicate that this layer has different alignment, and this alignment is called D. We can no longer see all the void spaces created between the two layers. In order to overcome this problem, we will make the second layer transparent. Now we can clearly see the two different types of voids created by these two layers. These are called tetrahedral voids, marked by the letter T. And these are called octahedral voids, marked by the letter O. The tetrahedral voids are created by four states. First, we make the spheres a bit smaller in order to understand the shape. Then we join the center of the spheres by straight lines. The shape is regular tetrahedral. So the void is called tetrahedral. The octahedral voids are created by six spheres. Here also we make the spheres a little smaller than joining the center of the spheres to get the shape. The shape is a regular octahedral. Placing the third layer. This can be done in two ways. These are the triangular voids of the second layer that are not involved in making octahedral voids of the first layer. By placing the third layer above these voids is one way of placing the third layer. If we do this, we can see that the first and the third layer have the same alignment A. With similar reasoning, we keep a fourth layer atop the third layer and see that the second and fourth layer have the same alignment B. This pattern of close packing is called ABAB type packing. We make spheres with smaller and joint centers with straight lines to understand the shape. It is my belief that this is the unit cell of this close packing because it is the smallest unit that may be repeated on the entire crystal. The top of this unit cell has the shape of a rhombus having gamma equal to 120 degrees. 3 such rhombus form a hair cell. For a better visual cognizance, this shape is taken as the unit cell of this close packing, which is called hexagonal close pack or simply 8CP structure. Another way of placing the third layer is to cover the octahedral voids of the second layer by placing the spheres of the third layer above the octahedral voids made by the first two layers. The alignment of the third layer is different from the first two layers, and so the color of the spheres have a different color, that is green color. Let this alignment be called C. Using the same reason, we can cover the octahedral voids created by the second and third layers by a fourth layer. It will be found that the fourth layer has the same alignment as the first layer. So this pattern is called ABCA type pattern. Now again, making the spheres a little smaller and joining their centers by straight lines, we get the shape of this pattern like this. The unit cell of such packing is this. This is nothing but a place of cubic lattice. So this type of packing is called cubic close pack or simply CCP or even FCC structure.
It's not supposed to be that. Wait a second. Okay. Any questions about that other than the accent? It's kind of hard to follow.
I wish I had more volume out of this thing too. Okay. Let's move to the next slide. No. Next slide. There we go.
Yep. Okay. I wanted to extract this bit of information from all that. I thought this was a good video because it started very simply with linear arrangements, and then it went to two-dimensional, and then three-dimensional. And the takeaway from this is that this way, this close packing model correlates to the unit cell in some way. This one is obviously face-centered cubic. This one, hexagonal close packing, is a little more difficult to follow because we didn't talk about a unit cell that was related to this. I think what we have here is a few slides that are talking about the same thing the video did. And this one is, let's see, ABAB. So it'd be this one, hexagonal close packing. And it all depends on where that third layer goes as to whether it's this one or this one. Does it go over the tetrahedral voids or over the hexagonal voids? There are two types of voids in there. For two layers create two types of voids. ABCA gives you, goes over the, let's see, ABC, okay. This one placed the third layer over the tetrahedral voids, and this one placed it over the hexagonal voids. So that's the basic difference between the two that gives you that the variation between the two types of packing models. Okay, so this hexagonal close packing, this is another illustration where you get a face-centered cubic derived from the ABA. Wait, yeah, ABA. And the cubic, okay, this author, I don't know if you caught it or not, when he started talking about this one, he says, I believe. This was his interpretation of the data. But the authors of the textbook say ABCA here. No, this is the face-centered cubic. That's right. That's right. Hexagonal close packing. Let me back up. Hexagonal close packing. This also produces a face-centered cubic. Right? According to the authors, this also gives you a face-centered cubic unit cell. But I like his explanation better. It's just that we don't have a unit cell like this in the description prior to the video. All right, so we'll have to talk about this a little more. When we start working problems, if there are problems in there that require this type of interpretation, then we'll deal with it. Otherwise, I must not have thought it was that important. Okay, so now there's a discussion of coordination number. So what does coordination number mean? If you focus on one atom, how many other atoms are in its vicinity? How many does it touch? And for this one, the cubic close packing, the ABA hexagonal. Okay, they're calling this also cubic close packing. Why would they do that instead of face-centered cubic? Well, okay, cubic close packing. Right, they're related to one another. So when we look at one atom and say how many is it touching, right? So it's got 6 around this way, 3 here, and 3 here. So its coordination number is 12. It's actually in the vicinity and touching 12 others. This is important for some types of chemistry where you want to know, at the risk of using words that we haven't defined, you want to know how many ligands are attached to that central atom. For instance, in hemoglobin, right? Had any anatomy and physiology, if you haven't, you know anything about hemoglobin, the atom that attaches to oxygen and carries the oxygen through our blood is iron. Well, iron is situated in a heme structure, molecule. We don't need to know what it is, but it has 4 points of attachment. Its coordination number is 4 for that iron atom. So this concept goes beyond what we're discussing today. This has a specific application in these packing models, but coordination number goes even further than that. Okay, so now we get back to our unit cell discussion where we were trying to define how many atoms are assigned to each one of the unit cells. Right? So since we've already talked about it, we'll just review. Right? Here's a face-centered cube. You got 1/8 of each of the corners and then half of each of the 6 faces, which gives you a total of 4 atoms assigned to that unit cell. So how many for a simple cubic? Right, we did that one already. 1 atom for a simple cubic. 4 for a face-centered, oh, body-centered. Where's the body-centered? Oh, we didn't do it. Body-centered was how many? 2. That's this. The corners plus 1 right in the center. So that's 1 plus 1 is 2. That math still works in chemistry in this class. All right. So what do we have here? Simple cubic structure. Metal has been identified probably through X-ray diffraction. It's been discovered that this metal crystallizes in a simple cubic structure. So what's the relationship between the radius of the metal atom and the length of an edge on the unit cell? Remember, simple cubic means all the corner atoms are touching. So the length of the edge is 2 times the radius of the atom. Let's see, do I have a picture? And no, I don't. So questions about, you can stop me anytime if you have questions. Remember when you have a cubic and you have an atom here and an atom here, they're touching. Right? So this radius here from the center out here is the radius of that atom. This is the radius of the atom. And the edge of the cube is 2 times the radius of the atom. Okay. These are important things to know when we start to do calculations. So for a face-centered cubic, you're going to have 1 in here that tends to push these apart. So we want to find out what's that distance right there, based upon this, this, and that. So I've got, I think in Blackboard I have documents in supplemental materials that explain how these things are calculated. But for now, just take my word for it, I guess. The length of the edge, if you have the radius of the atom, then the length of the edge is that radius times the square root of 8. And then one more, the body-centered cubic. Wait, face-centered, that's face-centered and body-centered is in here. Now, the length of an edge is 4 divided by the square root of 3 times the radius. Gives you the length of that edge. So you can look at each one of these as an equation. Right? If you know the length of the edge, if you want to know the length of the edge and you know the radius, you can calculate it. But if you know the length of the edge and you want to find the radius of the atom, you can do that too. Remember, anytime you have an equation with one unknown, you can solve it for the unknown. Okay, so here's an example. We have a silver metal crystallizes in a cubic close packing structure. That is, it's a face-centered cube. And the edge on the cell is 409 picometers. Right, so we know the edge. What we need to find out is the radius of the atom and how many of them there are in a unit cell, because we want to find out the density. So what we need to know is both what's the mass for a unit cell and what's the volume that's occupied. How much of that unit cell is occupied by a silver atom? If you can do that, right, mass, volume, you can calculate the density. So we start with, there are 4 silver atoms per unit cell because it's a face-centered cube. We knew that before. The volume of the unit cell is, let's see, d cubed, right? There's the cell edge length, right? So a cube is just 1 edge times height, breadth, width. Just multiply d 3 times. So it's that many picometers cubed is the volume of the unit cell. So we know it's this many picometers, and then you do some unit conversion. So what's a picometer? Well, let's see. A micrometer is 10 to the minus 6 meters. And a nanometer is 10 to the minus 9 meters. A picometer is 10 to the minus 12 meters. And why do we go, instead of meters, why do we go to centimeters cubed? Because the density of solids is reported as grams per cubic centimeter. Right? That, anytime you look it up, those are the units, grams per cubic centimeter. So we convert this, instead of meters, we convert this to cubic centimeters. Remember how to do that? Dimensional analysis. Right. If you have 1 picometer, what's the relationship? A picometer is 10 to the minus 12 meters, right? Okay. How about centimeters? Right. Got rid of that one. Here's meters, centimeters. Right. 1 meter is 100 centimeters. Okay. But we got cubic picometers, right? So we cube it, like that. And then 1 cubic picometer is how many cubic centimeters? You just do the calculations. Don't forget to cube. Cube that one, and that gives you cubic centimeters. Okay? That's how we got that conversion from there to there. See, this part, the coefficient of the number stayed the same. The only thing we had to convert was this part. Okay? All right, so now we know the volume of a unit cell. And now we need to know the mass. So what's the mass of 4 atoms of silver? Right? We did that in first semester, I believe. Let's see, what's the mass of so many atoms, or how many atoms in this mass? It's that dimensional analysis stuff that you love so much. 4 atoms, and then you have 107.9 grams per mole of atoms. But this is 1 mole per that many atoms. So notice how we're canceling units. So this mole is in the denominator, this mole is in the numerator. There's atoms cancel there. And that should leave you with grams. And then grams per cubic centimeter gives you 10.5 grams per cubic centimeter. Okay? And you compare that with actual measured density of silver. Come on, here we go. That was the actual measured density of silver. So our calculation agreed with the physical measurement of silver density. Okay, how do metals bond? Well, there are a couple of theories. There was an electron C model. That was the first one. It's like the metal atom, the nucleus of the metal is floating in a sea of electrons. Like this. The electrons are just all around. Well, the problem with that is it didn't explain very much. It was a starting point concept. In order to explain it, we need the molecular orbital model. Remember we got at the end of first semester? Thought you were never going to see that again, right?
Molecular orbital model. So we take a chunk of metal, and each atom has its atomic structure, and we combine all those orbitals into a molecular orbital for the entire unit, however much you have. Okay? When that happens, you get an array of molecular orbitals. If you only have 2 atoms, you get 2 right here. If you have more atoms, you get more and more. And what happens is they get closer and closer together in their energy levels. Once you get up to a mole, you basically have a continuum of molecular orbitals. So what does it take to move an electron from one to the other? Very little energy. That's why metals are very good electrical and heat conductors, because the electrons move freely from one level to another. And we're talking about levels of molecular orbitals for the entire group. It's not just from moving from one to the other. They can occupy any one of these energy levels with just the slightest input of energy. Okay, so we get what's called the empty molecular orbitals up here and the filled molecular orbitals up here, and they're very close in energy. So moving into an empty molecular orbital takes a very little input of energy. And they're organized into bands, like that. Okay, and because those electrons move freely, they're all bound together in these molecular orbitals. They have very strong cohesive forces in the metal. That's why it's difficult to, why you can build skyscrapers out of steel. Well, that's one of the reasons. The other reason is alloys. Because steel is an alloy. But what type of alloy is it? Well, there are 2 types. There's substitutional alloy, right, where you have a crystal lattice of a metal, and then you substitute some of those atoms with different atoms that give it different characteristics. Brass is an example, where you have copper and zinc. Yeah, copper and zinc. So your musical instruments, the brasses, are alloys of copper and zinc. Gives it different qualities. This is the substitutional alloy. Where you have that. You may have copper here, and copper here, and you may have another zinc over here. The interstitial alloys, you have to think about those voids in the packing. Those voids are large enough for some atoms to fit in there. And for steel, that atom is copper. Actually, some types of steel are a mixture of both substitutional and interstitial. To make it steel, you need carbon, and carbon fits in the voids. Carbon is a very small atom, so it fits in the voids in here. And imagine those are irons, and carbon fits in the void. And what it does is it locks the crystal structure, so you can't push things from side to side very easily, because that carbon in there holds things in place. Okay, there's your brass example, and here's steel with carbon stuck in there. Now, if you get more than, say, 0.5%, if you get 0.5% or more of carbon in your mixture, you have what's called high carbon steel. It's very hard, and you can make a sharp blade, very sharp edge, but it's very brittle. So if you want to have softer steel that is more durable, then you have to decrease the amount of carbon. Then in order to get the qualities they want, they plug in different atoms here, like manganese. Oh, let's see, what's some others? Don't want too much sulfur in there. manganese, some cobalt, maybe. Actually, they put in some more of those lanthanides and actinides. I don't know, maybe lanthanides. Actinides are mostly man-made anyway. Anyway, you get various formulations of steel. So when somebody says steel, the only thing they have in common is carbon. And from there, sky's the limit. Okay, the difference between diamond and graphite, they're both pure carbon. These are known as allotropes. In other words, an allotrope of an element is a different physical structure at the atomic level. So the diamond is this covalent lattice, whereas graphite each has layers. These are covalently bound layers that are stacked on one another, like plates. And they're held together with very weak forces, the London dispersion forces. So that's why graphite is often used as a dry lubricant, because these plates slide past one another. We used to squirt that stuff down the cable guides on a motorcycle, keep the cables moving smooth. And the nice thing about it is it's a dry lubricant. It doesn't attract dirt like oil would. Okay. So the molecular orbital model can be used for any one of these crystalline solids. The distance between the empty molecular orbitals and the filled molecular orbitals for diamond is huge. So that makes diamond an insulator. In other words, electricity, heat do not transfer well through diamond. Go from here to here. Whereas in a metal, the distance is very close, so it's a good conductor. So if you go to a jeweler's store and you have this rock on your finger and you're not so sure if it's the real thing, you know, the guy that gave it to you is questionable morals. So you want to find out if it really is a diamond. Say, a blue diamond might look like tanzanite. They're very similar in color. So you take it to the jeweler and they pull out this handheld device and they just put it right on the diamond and it measures heat conduction. Yet the diamond will not conduct heat very well. So it spits out a measure. Tanzanite will conduct much better. So put it on there. It's real, right? So you can trust it. Well, we did that with a gift that actually the person wanted to sell it to my wife. I said, okay, how much? I said, well, it's a tanzanite. So just pay for shipping. It's not worth much. So we did. Pay for shipping, sent it to us. Took it to the jeweler and says, look at our tanzanite. I said, wait. So they put the thing on it. It's a blue diamond. So the person that sent it to us doesn't know the stones. So we immediately called up State Farm and said, we need a rider on our home policy to cover the value of this thing. We had it appraised. Anyway, so these atomic solids can form different structures. And remember when we were talking about blending molecular orbital and my mind's gone blank. I hate it when that happens. I'll think of it in a minute. This is an example of graphite, right? Hexagonal structure, and it's got these free p orbitals sticking out here. Well, those p orbitals overlap, and actually they form a donut above and below the structure, and that adds to their stability. But it doesn't offer any strong bonding between layers. Oops, wrong direction. So it's a ceramic. Let's see. We have to get close to the end of this chapter. Oh, no, we have colligative properties. Okay. So we'll breeze through this. What's a ceramic? Well, ceramic, when I was a graduate student, I had a professor who was serving as an advisor on a different project. And I was investigating manganese in soils. So I was extracting them with various liquid concoctions. And I said, how do I refer to these things, right? Do we know what's happening when this extractant goes into the soil and pulls something out? He says, no, we really don't know. Call it operationally defined. So that was the catch-all term. Ceramics are operationally defined. They're not defined so much by their internal structure as by their characteristics. How do they behave? Ceramics are usually non-metallic materials. When they form, they're very strong, but they're brittle. Right? Think of a coffee cup. Right? It's strong, or a china plate. Very strong, but if you hit it the wrong way, it shatters. So it's brittle. They're very resistant to heat, and they resistant to chemical attack. So they're stable. The fancy word for that is refractory. They're refractory compounds. And they're usually formed by taking clays and heating them to high temperature. And they undergo a reaction. I never have had this one defined very well either. It's called a pozzolanic reaction. So if you're interested, you can look it up. But I haven't found any good sources for that. And it changes the structure of the clay or whatever else is used that goes into that. There's a, let's see, where's on the way to Summersville, cross over the bridge, and this either the first or the second exit on the left, you can go over there to a pottery shop. A man and his wife have a pottery shop next to their house, and they make stuff. We went in there one time, looked at it, got a couple of cups, and saw their operation. And they throw clay and then glaze it with something and stick it in the oven at high temperature, and voila, you got ceramics. How about semiconductors? What's a semiconductor? For the longest time, electricity was defined in terms of conductors and non-conductors. There's those that conduct electricity very well, like metals, like copper wire, and non-conductors, like the insulation they put around the wires. Initially, it was a plant-based product called gutta percha that worked very well, and now we use, of course, synthetics, much better. But there's a class of, actually they're elements that are semiconductors. In other words, sometimes they act like conductors and sometimes they act like non-conductors. Depends on the circumstances. And that's useful for our electronics industry. And they come from the metalloids. That's not going to see me over here, but right, follow this line right here. On either side of that line are the metalloids. And sometimes they act like non-metals and sometimes they act like metals. Those are the semiconductors. And silicon is the one we use for consumer electronics. You can use others like germanium is a good one, and it's more stable, right? So it's very expensive. So if you're going to build a microchip for a satellite, like a defense satellite, you may want to build it out of something that's a little more durable, like cosmic rays. Cosmic rays are always flying through. They can go through and interrupt electronic structure in your devices. So you either shield them or you build something that's more robust. Well, what's an N-type semiconductor? Well, you take the element, your base element, and you dope it with another element. So an N-type semiconductor, and we're going to use silicon as our base. So silicon has a certain number of valence electrons. It's got 4. 4 valence electrons. Okay? So if you dope it with phosphorus, phosphorus has 5 valence electrons. So in positions in that crystal lattice where the silicon would be, it's a substitutional alloy actually. You put phosphorus in there instead, and you get an extra electron. That's the N-type, or negative, semiconductor. And that electron is free to move, more freer to move than these others. If you want a P-type, then you substitute something with fewer electrons, like boron. Use boron, it has 3 valence electrons. So you're deficient 1 electron, and you get a P-type. And in the semiconductor, these are referred to as holes. They're positive holes where you're absent an electron. Okay. And there's an explanation. So this one's doped with arsenic, which should be an extra electron. It would be an N-type. And this one's doped with boron. It would be a P-type. Okay? And those are the things that move, the electrons or the holes. And they don't move very well, but they're controllable. You can put one of these together with another one and produce an electronic device. Okay. So that's our electronics discussion. The takeaway there is just to understand how the P-type is made, how the N-type is made. All right. Ionic solids. Ionic solids are very stable solids with high melting point. It takes a lot of energy to overcome the electrostatic attraction between the ions. So there are 2 things that determine the difference in melting points of one ionic solid versus another. So here is an example of sodium chloride. Right? Sodium positive ion is positive because it lost an electron, so that means it shrinks, it gets smaller. Where chlorine gained an electron, it ballooned a little bit. That's why chlorine is bigger than sodium in this example. Magnesium is lost 2 electrons, and oxygen gained 2 electrons. So the difference between these sizes is much greater. The 2 things that determine the attractive force and thus the melting point for an ionic solid are charge. What's the charge difference, right? 1 positive, 1 negative, or 2 positives and 2 negatives. So you have a stronger attractive force here based on charge. But also the distance. Remember Coulomb's law? We talk about that? We didn't talk about that. Coulomb's law just says that the force of attraction between 2 charges is based upon the size of the charge between the positive and negative, and the square of the distance between them. So as they get closer, the force increases. It's kind of like Newton's law of gravitation. The closer you get, the stronger the force. So we get these 2 charges that are greater than these, plus they're closer together, right? The distance between their centers is 212 picometers versus 280. So the melting point of magnesium oxide should be much higher than sodium chloride. Let's see, we get that data? Oops. No, we didn't. All right. I ought to stick a number in there, melting point. Melting point for this is much higher than this. For those 2 reasons, charge and distance. Okay. The 3 types of holes, right? This is the 2-dimensional model that our Indian friend was talking about. Right? There's a triangular hole. If you look at just the 1 layer, oops, wrong direction. And then if you go to 3 dimensionals, you stick another atom up here in that slot, and you get a tetrahedral hole. So that's the 3-dimension version. And then if you
if the second layer fits into a different hole than this one, there we go, fits into a different hole than that one, right? There are two different types. Then you get a hexagonal hole. If the second layer is arranged differently, it's actually slid sideways. You either get a tetrahedral hole or an octahedral hole. So, what about the size of these holes? Well, if we're only looking at one dimension, the trigonal hole on one layer is the smallest size of hole. Tetrahedral is the next largest, and octahedral is the biggest. So let's look here. So the space in here is bigger than the space for the tetrahedral. That's the takeaway from these slides. The relative size of the holes. All right, this is just straight out of your book. Properties, put all the properties together for these types of solids. The atomic solids, they're either network, metallic, or group A, noble gases. Then you have molecular solids and ionic solids. And you can compare the types of bonding that you see in them. There may be multiple types of bonding. And the typical properties and various examples. And one thing that I will call attention to, the molecular solids, they're typically soft, whereas the other types of solids are hard. Well, metallics are a range of hardness. Network solids, group A is irrelevant. Ionic solids are very hard, but these molecular solids are soft. And also, there's one other characteristic. These molecular solids, instead of having, if you take sodium chloride, and you say, over time, as you heat it up, there's the temperature. Over time, temperature is increasing. No, that's not a good example. I mean, that's not a good graph. Okay, let me put it this way. I tried to put it in a graph. The transition between solid to liquid is very sharp at the melting point. So when you reach the melting point, everything goes solid to liquid, just like that. Whereas with molecular solids, when they go to liquids, they have a very broad melting point transition. Some of it will turn liquid, and then it'll migrate gradually as the temperature increases. So it's hard to find a very, very defined melting point for molecular solids. And we'll see that in the lab when we do melting point depression lab, because we're going to use molecular solids actually. So you sort of have to guess, your best guess for melting point there. Okay, another property. That was melting point. This is vapor pressure. So you typically find vapor pressure applied to liquids, liquid transition to gas. You can get vapor pressure from solids, but it's almost immeasurable. So we're talking about liquids here. So you put this liquid in an Erlenmeyer flask and you stopper it. Initially, all the movement from the liquid to the gas phase is one direction. You get some that have sufficient kinetic energy at the surface to migrate into the gas phase. But eventually, as long as the stopper's in, you start to get return. these gases return, and it's a dynamic process. And you reach a point under a certain pressure in here where you get return and vaporization are equal in rates. And that's where the vapor pressure occurs. So vapor pressure will be higher for some liquids than for others. And the reason it's higher for others is the intermolecular forces are lower. So water, which is a hydrogen bonded compound, will have a relatively low vapor pressure because the liquid holds things in. Whereas ethanol, which is hydrogen bonding, but it's not as strong as water because water's got 2 hydrogens, whereas ethanol's only got 1 hydrogen stuck off to the side. It will have a higher vapor pressure for a lower molecular force. If you have something like hexane, it will have even a higher vapor pressure because the forces holding hexane molecules together are much lower. They're London dispersion forces. So this is what it would look like. The rate of condensation. Condensation is the expression of return a gas to a liquid. And vaporization is the other way around. So vaporization rate is constant. But the condensation rate actually increases as you put more of the compound in the vapor phase. They eventually meet. And that's when they're at equilibrium. Okay. What's the vapor pressure of water at 100 degrees centigrade? Well, if that's not worded quite right. The boiling point of water is 100 degrees centigrade, and the only time that happens is when the vapor pressure is 1 atmosphere. If you change the external pressure on water, then the vapor pressure will be different. So if we go to Denver, which is a mile high, water will boil at a lower temperature. The vapor pressure is higher because there's less resistance to the movement of water into the vapor phase. Okay, this is another example. So this is the mercury barometer, right? If there's a vacuum up here, this measures the air pressure. 760 torr is 1 atmosphere at sea level. If we put some water up here, then it's going to resist. It's going to put some back pressure, right? And this vapor pressure builds up, and then the difference between 760 and 736 is 24 torr. So the vapor pressure of water in that circumstance is measured at 24 torr. Ethanol would be 65 torr. Right? The intermolecular forces are lower, vapor pressure is higher. And this is diethyl ether. Right? The example we saw earlier was dimethyl ether. This is diethyl ether. And it's very low intermolecular forces holding it together, so its vapor pressure is massive. Okay. So this is a diagram of vapor pressure's dependence on temperature. Water has this curve, right? So when it reaches this point, at 1 atmosphere, it's boiling. But the boiling point for ethanol is actually 78.4. It takes less energy to liberate ethanol molecules from the inside, internally from the liquid. It's fighting 1 atmosphere pressure. And diethyl ether is even lower. In fact, if you poured diethyl ether on your hand, it would vaporize like that, because what's body temperature in Celsius? 37 degrees. That's 98.6. 37 degrees Celsius, body temperature. You put that stuff, just drip some in your hand and it'll flash. Don't breathe too deeply though. Just hit the floor. They used to use that stuff as a anesthetic for operations. That chloroform.
Okay, vapor pressure versus temperature is based upon the Arrhenius equation. So this is Arrhenius' original equation, and it's based upon, this vapor pressure is based upon this proportionality constant, and then E, remember E is the base of natural logs. It's like 2.178 something, something, something. E to the power of enthalpy of vaporization and the temperature, and then there's the gas constant. Okay? So if you know the enthalpy of the reaction and you know the temperature at which it's occurring, you can calculate the vapor pressure. But that's a little difficult to use. So we generally make a transformation, and then we end up with this one. The natural log of the vapor pressure equals minus the enthalpy divided by R, and 1 over T plus this C. So what does that mean? Okay. If you look at this equation, what does it look like? Looks like a straight line, doesn't it? Y is the log of the vapor pressure. Okay. The slope of the line is delta H over R, actually negative. There's your slope. This is X, right? That one, that one, that one. And B is Y-intercept, whatever it happens to be. So what that means is if you do experiments and you measure vapor pressure at different temperatures for a pure compound or a pure element and plot them, then the slope is going to be negative. And it's going to be, it'll be like this, log P, 1 over T, and it'll be in there, and the slope will equal that. So what does that tell you? When you find the slope, you can find out what the enthalpy of vaporization is. That's how they do it. They just measure 3 or 4 points, plot it, and there you go. I think I called that the wrong thing before. Clausius-Clapeyron are the responsible parties for this. Here we go. Well, this particular equation is Clausius-Clapeyron. This one's easier to use if you know what the vaporization, the enthalpy of vaporization is. Then all you need is the vapor pressure at this temperature. Then at this temperature, you can calculate what the new vapor pressure will be. And notice that R is this value. It's not the one with liter atmospheres. This is the one with joules. Right? So you have to be sure and use the right universal gas constant. This is the one with energy value in it. The other one is, I can't remember what it is now. Okay, so if we have a vapor pressure of water at 25 degrees and 23.8 torr, and the heat of vaporization of water is this value, kilojoules per mole, then what's the vapor pressure of water at 65 degrees? Right? Just use the Clausius-Clapeyron and solve for the unknown. And the new vapor pressure will be 194 torr versus 23.8 torr. You went from 25 degrees to 65, so naturally you would expect the vapor pressure to go up. All right, this is a phase change curve. And it's typical. It's not the only one, but this example is for water. What you will see is as you heat, right, this is like a time factor, you're constantly adding heat and the temperature is going up over time, okay? So you'll notice that when you have pure ice, temperature is gradually increasing, the solid. When it reaches 0 degrees, it starts turning to water. But it all doesn't turn to water at one time, especially if you have a lot of ice. So what happens is the temperature stabilizes right here until it's all converted to liquid, and then the temperature starts rising again. And when you start making steam at the boiling point, then it stays there until all the water's gone, and then the steam, you can heat the steam. So what's happening? Well, during this phase here, these slope lines here, the heat that you're adding is there to cause an increase in kinetic energy of the molecules in that phase. So they just get more active, more violent. But once you reach this point, all the heat you put in is used to break bonds and make the new phase. So the temperature is stable here until you get all of them into the next phase. And then they go up like that. Okay? Let's see. All right, so we talked about the enthalpy of vaporization before with the Clausius-Clapeyron problem. But you can also measure the heat of fusion. The heat of fusion is how much heat does it take to melt a solid? And this is how much heat does it take to convert liquid to gas. Now, this one's always going to be larger for any given compound. The heat of vaporization is going to be larger than the heat of fusion. Simply because here you only have to break bonds and allow the molecules to slide past one another, go from solid to liquid. This one you've got to completely separate them into gas. It takes a lot more energy. Okay, we can also look at phase changes in another way. These are some points, but I'll call your attention to them here. So here's a phase diagram, temperatures on this scale, pressures on this scale. Okay? The region of the graph here at these temperatures and these pressures, over here is all solid. Right? So as the pressure goes up, the temperature can get higher and still have a solid. In this area, you have liquid phase. So at this combination of temperature and pressure, you get liquids. At this combination of temperature and pressure, you get gas. And these phase diagrams can be very, very complex. This is a simplified version. You can have different types of solids that form, and you have interface lines. That's what these are, interface lines between solid and liquid. So if you start from over here and you say, okay, I'm going to maintain this pressure, but I'm going to increase the temperature. So eventually you increase the temperature, and there's where it changes right there to liquid. But if you have temperature up here, it won't change to liquid until you get to a higher temperature. Or it won't go from liquid to gas until you get to this point. Okay? So these are phase boundaries based upon pressure and temperature. Now there's one point on this graph where all three, and along this line, you can have solid and liquid together at the same time. That's that flat region from the previous diagram. Or you can have liquid and gas together here. You can have solid and gas here. Right? When would you have solid and gas together? A solid that sublimates, like dry ice, goes straight from solid to gas. It occurs down here in its diagram. There's a point on here where you can have all three phases together. It's called the triple point. So at this pressure and this temperature, you can have solid, liquid, gas all together at the same time. There's another point I'll call your attention to, the critical point here. If the pressure gets high enough and the temperature gets high enough, you go into a region up here, this line stops. And all this region up here is occupied by fluid. You can't tell the difference. Is it liquid or gas? We don't know. That's the critical point. That's the basis for supercritical fluid extraction, if you've ever heard of that. It can be used to extract caffeine from coffee, right, and leave all the flavor molecules in place, so it's
tastes better, make decaffeinated coffee. We used to use it in the lab to extract samples, metabolites from within cells of plant tissue. Supercritical fluid extraction is gentler than like heated methanol reflux. And then most of the time, not all the time, but most of the time, supercritical fluid extraction is done with carbon dioxide. So you don't have any, once you've extracted, you do it at high temperature and relatively high temperature and very high pressure. Then once you have finished, when you release the pressure and you open up your container, you've got your extractant down there and no carbon dioxide left, because at room pressures, temperatures, it's gone. It's off to contribute to global warming, right? Tell you where I stand on that topic. Anyway, notice that for water, well, let's back up. For this one, usually the slope between solid and liquid is positive, slopes to the right. But for water, it's different, slopes to the left. And that probably has to do with the way the crystal structure forms when ice forms from liquid. So if you were to start here at this temperature and increase the pressure, you can go from solid to liquid. And for the longest time, that was the explanation for ice skates, how they work so well, how they slide on ice, because you put all your weight on that narrow blade and you increase the pressure so high that you form a layer of liquid underneath the blade. Now, I think they've done experiments that kind of debunk that, but it's a nice thought. Okay, so as intermolecular forces increase, what happens for each of the following? Boiling point. Boiling point increases as these forces increase. Viscosity increases, surface tension increases with an increase in intermolecular forces. Enthalpy of fusion, how much energy does it take to melt a solid? Freezing point increases. Vapor pressure backwards. As you increase the intermolecular forces, the vapor pressure decreases because it's holding those liquid atoms and molecules in the liquid phase. Stronger forces decrease the vapor pressure. Heat of vaporization increases. This is the only one that works inverse. The rest of them are direct proportion to increasing molecular forces. Okay, chapter 10. You take a break. You already know that I'll just keep talking.
I need
So you have to call me on break sometimes.
I need the bathroom before you start next.
Okay. See if I'm still recording. Yes. I've done this sometimes where it's go through the whole lecture and it's not recording. So I got to, after class, I come back in here and do the whole lecture over again. Okay, chapter 11. Properties of solutions. All right. Okay. And I've learned not to pause that for breaks. Is that your name in Mandarin?
No, it's chemistry.
Chemistry.
Yeah, a little chemistry. So I think it's you are straight.
Okay.
Well, straight.
Okay. let me check my time here.
4:45. We got 5 minutes left.
Yeah. And then we go into the lab.
Yeah.
What I may do before we start on this chapter, we may talk about the lab a little bit, and then we'll do the chapter.
So we're doing the lab in this room.
I can show you the lab, but it won't do you any good right now,
Fine.
because we're not going to do any labs today.
Okay, so we're just gonna talk about the lab. Yeah, so this.
Yeah, we'll pull out the syllabus and see what you need. In fact, let's see. How about Blackboard? Okay. So we're going to talk about the lab just a little bit, so I don't forget. Run out of time. Let's get my copy. My copy of the syllabus. Oops. Here we go. All right. So contact information is the same. Course materials, you don't need a textbook of any kind. You need a calculator, of course. And you need the composition book. Let's see. Maybe I can put the syllabus up here. I didn't bring a copy with me. So I have to show you a picture. In fact, I'll tell you what. You got a book on you. Oh, here it is. Not paying attention. This is the kind of lab notebook I want you to get. It's like a bucket. You have one already? Is that a composition book?
Yeah, it is.
Okay, it needs to be quadrille
Right. Yeah, right.
graph paper. Yeah. They're a buck at Walmart, or I can sell you one for a buck. I go through there. My students have had trouble finding them sometimes, so I always keep a stash with me, and that saves you the trouble if you want. You've already got one. Okay. That's right. No breach. Right. So you want to go on your own, or you want to buy one?
Yeah, it's fine.
Okay. If you have a buck with you, pay it later.
I won't have, but I'll be Monday, I guess.
And so that's what you're going to need. You'll also need a lab coat like this, at or near knee-length. We have eye protection in the lab, but those things have been there for years and then maybe kind of fuzzy, scratched. You may want to get eye protection of your own. You can get either full goggles or polycarbonate over glasses with shades on the side. Those work for the types of labs we're going to be doing. And we provide the gloves, so you don't have to worry about that. Okay, let's see. All right, so how do you prepare your lab notebook?
Let me see if I've got those instructions in Blackboard. I usually print those out and give you copies. But I wasn't able to this time. So let me go into Blackboard. Okay. And let's see. Here we go. That's what you'll see. Okay. So it's always start here to begin with. There's the schedule, syllabus, my schedule, lab exercises, lab notebook and reports. This folder has information in it that you'll need. Pay attention to everything you read. The other stuff is optional. Let's see. Okay, I thought I had a description. Lab notebook format. Maybe I ought to make this one red. Come on. Well, hey. Let's try it this way. Oh, I do have a sample. Maybe that would be better. Let's try this one. I've also got sample reports, formal reports, so to show you how to structure them. We're going to have a lab next week on the molecular weight by freezing point depression. We start off simple. And as a general rule, the lab report is due the next time we go in for a new lab. So if it's the next week, the lab report's due that week. If it's a 2-week jump, and most of them, yeah, all of them are minimum 2 weeks. So you've got an extra week. We won't have a lab. We'll have one next week, but we won't have one after that. And the formal report then is due, has to be typed. Has to follow a certain format, and that's what I'm trying to show you now. But actually, I'm trying to show you the lab notebook first. Here we go. Come on. Oh, this computer is so slow. There. Okay, so on the front cover, you want to identify this notebook as yours. You got your student name right there. Then you have what course is it and what semester is it. That's minimum information. Okay. Let's see. All right, then you'll have table of contents. Oh, First thing you want to do is go through, number every page.
Okay. This one is 1, and it's always in ink, indelible ink. 1 here, 2 there, 3 there. So all the odd numbers are right-facing pages, and all the even numbers are left-facing pages. So all the way to the end. Be meticulous, because you might get to the end, and I'm thinking you 200 pages. So if you're off somewhere in here, then it'll be, you might end up with, if you go through here and you say, you start to write an even number on this side, you know something went wrong. Okay, but do that first. And then set up a table of contents. Just write table of contents, and what do you put in the table of contents? In the table of contents, you want the name of the experiment and the page that it starts on. This student chose to put from to, but you don't have to do that. You just put where's the page, first page it starts on. And then for the next experiment, where's that page? Just go down there like that. And this will fill in as the semester progresses. So in the first place, you just number the pages, identify, and set up your table of contents. And then, of course, for the first experiment, you'll have to go over here maybe a couple of pages over, and then put the title. Let me scroll down to the next one. This student chose to go to page 5, probably. Yeah. So there's the date, the name of the experiment, and then you put information in the notebook so that you come in the lab and you work the experiment from the notebook only. You don't refer to the hard copy method, only your notebook. So that means you've got to write it in here in sufficient detail so that you know, so that you can do the experiment from your notebook. So you have, and also, if you put it in here in this order, then writing the formal report is easy because you go to your notebook and there's the information. Right? Got your objective, got materials that you're going to need, got any pre-lab questions that you've answered. Of course, you answer those before you come into class. Right, there you go. And you skip that's another thing, you skip the even pages. You only write on this side. Leave these blank. The reason for that is, if you make a mistake over here and you don't have enough room to correct the mistake in here, go on this side. Okay? And you always, when you make a mistake, cross through it and write the correction. You don't try to erase it. And if you make a mistake on a whole page, you just, and either if you got room, go to the next page or go over here. Or if you need to draw a graph, that's where you do it. Okay. The next odd page is here. Then your procedure, step by step. What are you going to do in the lab? Now, at this point, you're saying, do this, do this, do this. Right? That's not exactly how this was done. So this may be a poor example. But this can be straight out of the method. But if there's something in that method that's not quite detailed enough for you, you elaborate. Okay, so that you can do the experiment from your lab notebook. And then when you go into the lab and do the experiment, you make notes here in this section saying, all right, this is what the method said, but this is what we actually did. You make corrections as you go. Because when you write your report, you write the procedure in passive past tense. This is what was done. Okay, not what to do. In other words, you don't go to the printed method and regurgitate it in your report. You get marked down severely for that. You write what actually happened. Okay, and there's a sample report in Blackboard also that you can look and see. All right, this is what the instructor is looking for. There's also a rubric in there. I'll show that to you in a second. That I use for grading purposes. Okay, set up a section for data. In other words, when you collect information in this lab, you want a place to put it. And you want to make reserve a place for that in your notebook so that you know something goes in there. And if something goes in here and you're down here putting information in, why isn't there something up here? That should cause you to stop and say, did I miss something? So you have a place, I like tables, but you can use lists and underline as a place to put numbers or observations. So you need a data section. And here the data section was specific to one activity, and we have a second activity. And this person took their data and produced a graph in Excel, and then cut and pasted it. Right. So they printed out in Excel, they cut it out, pasted it in here. When you do that, if you paste anything in your notebook, which is fine, then across the margin, which they didn't do, across the margin of the boundary between the paste and the underlying page, you initial or sign so that it overlaps both of them. That's so that if something happens to that, if it's missing and you see only half your signature there, you know something is fishy. Let's see, what else? Okay, more data. Calculations. You need to do calculations. There's a section on that. Let's see. There may be additional laboratory questions. The pre-lab questions need to be answered before you come into lab. The other questions you do afterwards. So just create a section in your book with enough space to do the answers. You don't have to answer until afterwards. Some of them require calculations, so you're not going to be able to do them anyway. Okay, so there we go. And then there should be a section on conclusions. Okay, I probably graded this one down for that. You should have a section on there for discussion and conclusions. What summary? What did you learn from the experiment? What conclusions can you draw from the experiment? Because in the formal report, there's going to be a section required for that.
When you grade our lab notebooks or do checks, are you going to do it during lab or?
Probably. Yeah.
I just didn't know if you don't get them until the semester or because when we did it online, I had to send pictures.
No, this is different. Yeah, I'm going to look at it. I'm going to look at it up close and personal. So what I want to see, the first check is just get your notebook ready. Right? Have this done right, number every page, set up the table of contents with the first experiment in this case, because that's the first time we'll meet again. And then have your first experiment laid out and ready to go. And that'll be your first grade for lab notebook. Then there's, if you want to know something about the report, what's the report format? Let's see. Here are instructions for the lab report right here, but it might be more instructive to look at both this one.
We got two to go from. Let's look at this one. This is a sample report with the rubric graded. Let's see. Here we go. That's kind of on the side, sideways. Let me see if I can shrink that so you can see it better. Come on. About 75%. Okay. I don't want to make it too small. You won't be able to see it. But this is a rubric, and what I'm looking for are these things down the left-hand side. If you turn your hand sideways. So do you have every section in the report that's supposed to be there? All right. If you're missing a section, then I'll grade down.
And how do you know what sections? Well, that's what the sample report's for.
This person had everything plus a little extra. How about your spelling and punctuation?
I mean, so many points students lose on that one simply because they don't use spell checker and they don't proofread it.
Grammar.
This is where I want, especially for the procedure, to be written in the passive past tense, right? 300 milliliters of ethanol were measured in a graduated cylinder. That's passive past tense. It wasn't, you don't say, we got a 300 milliliter, a 500 milliliter graduated cylinder and put 300 milliliters in it. Right. We, that's first person. I want third person. Passive, past tense. What was done. And the report that follows this will show you how to word it. Let's see. Appearance and organization. Most of my students usually get this one okay. Procedures, are they there? And various conditions. Right? Farther to the right gets you fewer points. If you go all the way to the right, you get no points for this item. Data, analysis. Do you have a summary and conclusions in there? And does the summary and conclusions say anything? Right. It doesn't, believe me, I've had students say, we had a lot of fun. Hey, I circled that one right there. Maybe this one, because they did actually have it there. But it didn't take much thought. And then scientific concepts. So all these different things I'm looking for in your report. The reason for the structure like it is just to, it mimics a peer-reviewed article in a scientific journal. The structure is very similar to this, not exactly, because this is a teaching situation, but has similar elements in it. And I want you to get used to defending yourself this way on paper, because I don't know about other places, but in government we say if it's not on paper, it never happened. Okay, so the report itself has a title, it has the author's name, your name. If you have any lab partners, put their names here too. And then details on at least the date of the experiment. This person went overboard, which is fine. What you want to do is set up your notebook so that you can take your notebook and easily produce this. So if you do all your thinking, calculating in your notebook, when it comes time to write your report, it's easy. I mean, unless you hunt and peck. Do y'all, both of you touch type? Hunt and peck. Well, I don't know. My son is a hunt and pecker, and he's pretty quick with it. I guess he's learned where all the keys are. But touch typing is the way I go since junior high. Okay, so there are your objectives. Right, there are the materials. Give me something on safety. What safety concerns are there? Right? Do you need to be concerned with safety? Well, if you don't, just say so. In this one, this is Boyle's law, so you had to be concerned with a pressure vessel exploding in your face. Right? Something like that. Procedures. This is what was done. The local air pressure was measured with a barometer located in the classroom. Simple. This was done. The local pressure was measured. The syringe cap was placed on the syringe. This student went into a lot of detail, which is fine, but it's the grammar that gets you there. Okay. I made some corrections, right, but it wasn't major. Then here's your data. Right? This is the format that would pass for a referee journal. This format. It's got everything explained. Any additional explanatory notes are down here in the footnote. Right? It's got graphs. Right? This is volume versus pressure. And this is a volume, inverse volume against pressure. Right? Remember Boyle's law? Inverse pressure, inverse volume versus pressure gives you a straight line. Let's see. Calculations. Pre-lab questions, you can put them anywhere. Right? Just be sure and identify them as pre-lab questions and the numbering system that's used in the document. So I don't have any trouble. I don't have to search around for what you're trying to answer. Post-lab questions. And then there should be a summary, conclusions and summary. Okay? This student actually put some thought into it. They actually cited works. Usually don't have to do that, but you can if you want. Guiding principle for your notebook and for your report. Anybody who picks up your notebook a year, 2, 3, 10 years later should be able to take your notebook, go in the lab and duplicate your experiment. It should have that much detail in it. You should be able to do it, right? When I used to work in research, I made my notebook as detailed as I could get because I knew at one point I'd have to go back in the lab and do that thing again because I knew my supervisor. But I would make my reports just as detailed so that I could take them. They were publishable, but I could also take them and go back in the lab and repeat that experiment myself. It had enough detail. That's what you're looking for. If you can't do that, then your report and your lab notebook are incomplete. Oh, that's the end of that. Okay. Let's see if there's anything else in Blackboard that would help. The only reason that I produced this document on plagiarism, I mean, everybody understands what plagiarism is in a liberal arts course like English or history. If, you know not to copy somebody else's work without giving them credit. But in sciences, plagiarism can also be, you don't claim somebody else's work as your own. So it doesn't even have to be published. If you claim that you did the work that somebody else did, that's plagiarism. And I've had some students do that, particularly if they were family members. Sometimes they have husband and wife or cohabitants partnering in the lab, and their reports would be word for word identical. It was obvious. So I had to create this policy on plagiarism, and that document tells you what I consider plagiarism to be.
I've even got a document in here, common errors in preparing a formal lab report. There's things to watch out for that you don't make the same mistakes. You may want to read that too. Extended character set is, let me see if it won't take too long to load. I usually hand a copy of this out in class. I know these characters are good for Windows-based. Yeah, that's kind of small. Expand it. That's what happens when you use a free application. Let's see, 100%. Maybe that's a little easier to see. But what you got here is when you're doing writing a scientific report, sometimes you need special characters that aren't on the keyboard. And you can either go to the character map and scroll through them and find them, copy paste. That takes forever. These are the most common ones used, and they're a little hard to see, but you've got inside Windows characters and DOS characters. I don't know, you're probably not old enough to remember DOS. DOS was before Windows, but it's legacied into Windows. So these work also within Windows. So what you do is hold the Alt key down, and on the number pad, you type in this number sequence, and you get that character like that. These are for Mac machines. Some of them work. I don't know if they all work. I just tried to pick out the best ones. And if you own a Mac, then you have my sympathies, because Apple products don't play well with others. So you get things like, let's see, there's delta, like if you're doing delta H enthalpies, things like that, there's your delta. If you're doing the measurements, you want micrometers, or there's the micro symbol right there. Or if you need a mid-sentence or a mid-dot between something, there's one. There's another bigger one down here. If you're doing square roots, there's you got your square root symbol. So there's several in here that play around with it and see if it works on your computer. But it's also in that same folder. Okay. Let's see. I need to waste any more time here. Okay, so let's go back here. There's our schedule for the labs. Notice this blank space in here. I've also put in non-class days. We're not going to meet on the 6th of September. That's Labor Day. So actually, you have 2 weeks between this one. We're going to do this experiment next week, and then you have 2 weeks to get that formal report done. So you have a little extra time there. Then come ready to do chemical kinetics. And so forth. So we have 6. We have 6 labs. Okay. Here are the lab exercises. Oh, I see. Yeah, I left this in here. This is when we were under COVID lockdown. I had my classes photograph or scan and send me their notebooks. So that's what this is for. You can ignore that and just bring it to class. Video demonstrations. All right. This is a consequence of the COVID lockdown. We did our labs online. So what I would do is I'd go in the lab and I have this camera and strap on my head, and like a GoPro, only cheaper. And I would do the labs and gather the data so the students could see what was happening, and then they would generate their reports from that. So I left them in the Blackboard course so that you could go in if you wanted to and look at it and see, all right, this is what we're going to be doing in the lab.
so you can actually see what's going to happen before you go in and do it. The first rule of safety in laboratory is prepare. If you're not prepared, you're just an accident waiting to happen. That's why I insist that you transfer everything into your notebook first, come ready to do it that way, because the simple act of putting all that information in your notebook should get you ready, geared up for that experiment. So these folders have each one of the experiments in them. Right? This first one. So here's the document. There it is. You can get to it here, or you can open this up. And there it is there. You get that document. That's your copy that tells you what we're going to do, how we're going to do it. And inside this folder is also a place to submit your report. So if you look right down here, attach files. So when you get your report ready, just say, browse my computer, find your report, and submit. Or you can hand me a hard copy. That's okay too. Just bring it to the due date lab and give me your hard copy and we'll be fine. And about due dates, the official policy is the day that we do the next lab is when it's due, but you can either bring it to lab or you can submit it by midnight that night and it's still on time. I've had students have their reports, and I trust the ones that I'm talking about, that just forgot to bring it. It's at home. So they got it to me by midnight, and that's why I know that they didn't just go home and generate the report offhand, because it was good quality and it had to be done ahead of time and ready to go. They just forgot it. So it's due by midnight the day of the next exercise. Okay. So each one of the labs will be like that. Exercise. What I like to do is have a hard copy printed out for you. And the week before, try to take a few minutes out of our class time and just discuss it a little bit and get you prepared for any quirky things that all labs have. I mean, it's one thing to study in the lecture situation and be able to work problems. And then when you go in the lab, it's like a completely different world. You need to know the theory, right? Why you're in there, why you're doing the stuff, but there's no substitute for hands-on. That's why I hated this lockdown so much, because it kept my students out of the lab. And that's a vital component. I mean, even though the course is only worth 1 hour, it gives you the experience you need to understand these concepts. All right. Okay, any questions? I'm going to exit that preview. And I'll just leave it out. We'll go to our, okay, well, I forgot I called this one up. This is lab notebook format. It gives you some details. Right, okay, there's this section right here. This covers all the stuff that I talked about. I want to be put in your preparing for the lab. Sections here need to be lined out for all of these items. Okay, so let's go to chapter 11. Here we go. Let's see, 11:30. And oh, yeah, the back page of your syllabus.
Oh, that's okay, go ahead. Just give it to me on the way out.
I just went ahead and read through it.
Okay. Issue, curiosity. Okay, chapter 11. We talked about liquids and solids. Now we're going to put some of those things in solution. Right? What constitutes a solution? Well, a solution has to be a homogeneous mixture. In other words, you have two substances, minimum, or more, and the mixture you retain the characteristics of each of the substances that are mixed together. In other words, for instance, salt water. You put salt in water and it dissolves, what's in there? Well, there's still salt and there's still water. It didn't change. They just went into a mixture. Right? So they have to retain their identity. But they can either be homogeneous or heterogeneous. Solutions are homogeneous mixtures. That is, anywhere you sample that solution, you will come up with the same composition of substances in there. Same amount of each one, proportionate to the others. That's homogeneous. Heterogeneous, if you sample in different places in that solution, or what you think is a mixture, you will get different compositions. For instance, if you try to mix sand in water, right, you stir it really fast, and you think you've got evenly mixed. Stop stirring, immediately it starts to settle. If you sample from the top, you get very little sand. If you sample from the bottom, you get a lot of sand. That's a heterogeneous mixture. Solutions are homogeneous mixtures. But they can be mixtures of different phases. They don't always have to be solid in a liquid, like salt water or sugar water. They can be gases. You can have two gases, right, form a gas solution. And that's always the case. Like I said before, you put two or more gases together, you always get a homogeneous mixture, a solution. Vodka or antifreeze is, well, let's use antifreeze. Ethylene glycol. Let's see, we're using terms here. We're going to define, or did we define those last semester? Solute and solvent. You remember what those are?
I remember talking about it.
Okay. The solute is the minor component. The solvent is the major component. So if you put a little bit of salt in a glass of water to make like a saltwater gargle, the salt is the solute and the water is the solvent. Okay, so in the case of antifreeze, ethylene glycol is the solute. And you put it in water in your radiator to keep your engine from overheating or freezing in the winter. That's one liquid dissolved in another liquid. And the product is a liquid. The alloys that we talked about, brass, you have copper, zinc is the solute, copper is the solvent. And when you melt them together, mix them up real good, let them solidify, then they produce a solid at room temperature that is a solution of copper and zinc. Carbonated water, there you have a gas, carbon dioxide dissolved in water. A gas in a liquid produces a liquid, a fizzy liquid. Seawater, right? This is what normally people think of as a solution, a solid dissolved in a liquid, right? Sugar solution, seawater. Like I made a solution for the hummingbird yesterday. Dissolved sugar in water. You can even get a gas
dissolved in a solid. When we hydrogenate on an industrial scale, polyunsaturated fatty acids, they put hydrogen mixed in with the fatty acid, and they use platinum as a catalyst. Well, the hydrogen dissolves into the solid platinum before the reaction occurs. That's a solution. This type of thing happens in your catalytic converter in your car too. You get gases dissolved into the surface of the precious metal that's plated on those ceramic beads in there. Actually, they may use a ceramic matrix now instead of the beads. Probably because when catalytic converters first came out, people didn't like them because they reduced the power of your engine. There was too much back pressure. So they quickly found out, shade tree mechanics, you just take a screwdriver, go up that catalytic converter, and poke a hole in it. And all the beads come flowing out. And then you patch the hole, and you still got the catalytic converter looking like it's there, but you still got your power. And of course, unburned hydrocarbons that come out your tailpipe. So that's why they started doing testing in some areas, like Atlanta, I think, for a long time. They may still do it. They stick a probe up your tailpipe when you go in for inspection. And if it doesn't pass, then you got to get the converter fixed. That usually only happens in big cities because that's where your major smogs occur. Okay, how do we express solutions? Right? If the concentration of your solute in the solvent can vary, it can be a different amount. Right? You could put a lot of salt in your water or just a little bit. Then you need a way to express that concentration. And these are different ways. Molarity is one, and we'll talk about these individually, I think. Yeah, we'll define them individually. Molarity, you can have a weight percent by mass, or you can have a mole fraction, right? So many moles of solute per moles of solution. Molality is related to molarity. Moles of solute in kilograms of salt. That's the one we're going to use next week in our freezing point depression experiment. Okay, molarity, designated by a big M. So a 2 molar solution says that you have 2 moles of solute in 1 liter of solution. That's what it means. So if we have 1 mole of sugar in 125 milliliters of solution, what's the concentration in molarity? Well, this is defined, moles per liter. So if you have 1 mole in 125 milliliters, that's not going to give you molarity because the volume is milliliters. It needs to be liters. Right. So you can do a dimensional analysis, or if you know, how many milliliters are there in a liter? 1,000. Milli. Milli means 1,000th of. So 1 milliliter is 1,000th of a liter, which means it takes 1,000 milliliters to make a liter. So this value is actually 0.125 liters. Right? I just took this number and moved that decimal. 1, 2, 3. Right? Then you can divide those and come up with the answer. While we're on the subject, when you write your reports, particularly write your reports, if you have a decimal out here by itself, like that, if you write it like that, it's wrong. That's what I call an orphan decimal. It needs to be bracketed, a placeholder. Right?
there, okay? I suspect that grade school and even high school teachers are telling their students that they don't need that zero out there. Well, they're wrong. You need that zero. Okay, so if we divide 0.125 into 1, that's just the inverse of 0.125. Right? 1 divided by the number. Gives you 8 molarity. 8 molar. That solution is 8 molar in sucrose, table sugar. And actually, you can add enough sugar into the solution that the solute amount will exceed the solvent amount eventually. But since you started off with a little bit of sugar and you just add more, we still maintain that sugar is the solute and water is the solvent. Okay. So for this definition, molarity equals moles, and that's my abbreviation for moles, little n, divided by volume in liters, right? That's a formula. So if you know 2 of those, you can find the third one. We just solved for this one. But what if you know this one already? 10 molar. And you want to know how much volume do you need to give you 2 moles of sugar? So you just substitute 10 here and 2 here and solve for that. Okay? So you need 2/10 of a liter to give you 2 moles of sugar out of that solution. Now, most of our glassware in the lab is not calibrated in liters. Some of it is, but most of the time it's in milliliters. So how many milliliters is that? 200. 200 milliliters. Move the decimal place. 1, 2, 3. 200 milliliters. Okay? And how many of those numbers are significant? 1, 2, 3. 3 significant figures. So if you write that, 200 milliliters, you need a decimal right there. Remember the rules of significant figures? That means all 3 of them are significant. You leave that out, only the 2 is significant. I don't know what they've done to this board, but I don't like it. It erases a whole lot better than the one I had at home. Okay, let's see, how are we doing on time? 12:50. Okay. Let me whistle. So, it's important to understand that when you're calculating molarity, it's based upon the moles of solute, not the mass. So you can have equal masses of different compounds that give you different molarities in the same volume. Here's an example. If you have 100 grams of sodium hydroxide and 100 grams of potassium chloride, and you dissolve each of those in 250 milliliters, what kind of molarity are you going to get? It depends on the molar mass of each one of these, because you can't calculate molarity with grams. You've got to convert it to molarity. Well, let's see, how did they get that? Well, dimensional analysis, 100 grams of sodium hydroxide is how many moles? Grams, moles, right? Cancel the grams, leaves you with moles. So how many moles is that? Well, we need to know the molar mass of sodium hydroxide, don't we? Right. So let's see. Sodium is about 23. I'm roughing it in here. That's 16 and that's 1 for hydrogen. So that's 40 grams per mole, roughly. So it's 40 into 100. 2.5, right? 2.5 moles. So it's 2.5 moles of sodium hydroxide in 250 milliliters, which is 0.250 liters. So that's why you get 10 molar sodium hydroxide. And you do the same thing for potassium chloride, only you have fewer moles of potassium chloride. See, and that gives you lower molarity because this number is bigger. Potassium chloride weighs more per mole than sodium hydroxide. So it gives you, you get a different molarity calculation. The molarity is very convenient to use in chemical calculations, simply because chemical reactions don't occur based on mass. They occur based on molecules and atoms, moles of things. Remember when we balanced equations, right? And you had to do calculations from one place to another, right? What's the outcome? You can't get from here to there with grams. You got to convert to moles first. Right? Chemical reactions are based upon numbers of atoms and molecules, not masses. So if you have a solution chemistry going on and solution reaction, then this comes in very handy. So that now you can calculate, if you know the volume of solution that's added together with another solution, you can calculate how many moles of the reactant go into that solution. Okay, mass percent. Percent is grandfathered into our system. Percent is a dimensionless number. Percent means parts per 100 parts. So parts of what to 100 parts of what? In the first place, what's your units of measure? Well, this could be mass, and this could be volume, or it could be mass. That's what this one is.
Sorry about it.
Yes, sir.
Air conditioner will be fixed tomorrow. The part came in, they're here today, but there's a fuse they have to overnight.
Okay.
So it's something to get done today. It's still a good one.
Okay. Are we doing okay?
Thanks.
That's all right. It happens. Or it could be volume. So whenever you see percent used as a measure of concentration, it should be followed by information as to how the percent was calculated. Is it mass, or by mass, it may say, or is it mass volume? So the solute is in mass and the volume is in the solute or the solution. That's the problem with percent. If you just say percent and you don't know something about how it was calculated in beforehand, then it could be anything. Okay, in this case, mass, weight, percent. Right? So mass or weight percent. That's probably because sometimes we use weight measurements instead of mass. For our purposes, mass percent is accurate. Mass of the solute divided by the mass of the solution. So if you combine 10 grams of salt, of sodium chloride, with 90 grams of water, what's the mass percent? Well, it's 10 divided by 10 plus 90. Because this mass is still there in the solution, right? Well, times 100. And that'll give you mass percent. So it'll be 10% by mass. This example is 5.5 grams of glucose and 78.2 grams of water. Didn't show the calculation. So 5.5 divided by 5.5 plus 78.2 times 100. Now sometimes you need to use mass percent in a calculation, and the percent isn't the most convenient. Sometimes you need to use the decimal equivalent. So what's the decimal equivalent of 6.6%? That implies 0.066 is the decimal equivalent. And that way you don't have to deal with this 100. Now you can if you want. All right. So another way to express concentration, mole fraction. This one is pretty neat. And it's very useful for gases. Mole fraction is simply, and this squiggly X with an A under it just says mole fraction of A in the total. So you need the moles of A and then the total moles of the solution. So if you have moles of carbon dioxide and the moles of water, then you can add them together to get the total. And the mole fraction would just be the moles of carbon dioxide divided by the total. And it is a fraction. It's always less than 1. If it's a mole fraction of 1, then it's not a solution, right? Because everything is A. Or if it's a mole fraction of 0, it's all solvent and no A, right? So it has to be a fraction between 0 and 1. So if we have a phosphoric acid solution, we have 8 grams of H3PO4, we can find out how many moles that is, right? Just use the molar mass of phosphoric acid and convert that to moles in 100 milliliters of water. And you just need to know, right, how many grams of water is that? Well, we're going to assume that the density of water is 1 gram per mil. That's what this is. So now you know you have 100 grams of water and 8 grams of phosphoric acid. You can calculate the moles of this one and the moles of that one, add them together for your denominator, put this one in the numerator, and you got your mole fraction. So it's pretty small. The other thing is, if there's more than one solute in there, and you calculate several mole fractions, then when you add up all the mole fractions of the solutes plus the solid, you should get 1. Yeah, the mole fraction of water would be whatever this is in moles, divided by the total, which would be that plus this. So you have to add in solvent too to get 1. Molality, that's the one we're going to be using next week. Molality, notice the numerator is moles of solute, same as molarity. Molality is this little m, is its designator. And the denominator, instead of being liters of solution, it's kilograms of solvent. Right. So if it's water, then if you have 1 liter, you've got a kilogram of water. But why do we use mass down here instead of volume? Any ideas? What happens to volume if temperature changes? Volume changes. Right? So if you try to do an experiment that's dependent upon temperature change, like freezing point that we're going to do next week, you can't use molarity because molarity is going to change with the temperature. You need something that's oblivious to temperature change. So that's why we use mass here instead of volume. Okay. All right. So that same solution has a different molality than molarity. Oh, no, it's mole fraction. It's definitely different than mole fraction. Okay. Theoretically speaking, how do we form a solution? This is a concept, a theory. All three of these things happen at the same time, but we separate them out so we can try to wrap our brains around it. Like I may have said already, nature just does what it does. It's going to go on and do what it does, rain if it wants to, not rain. Doesn't care what we think about it. What we try to do is wrap our brains around it, understand it. So any theory that we come up with has to agree with reality. Reality is what nature wants to do. Nature does it, and it's up to us to catch up, figure it out. This is one of the ways that we do it. So what happens? When you make a solution, three things happen. You've got to separate the solute molecules. Pull the solute molecules apart, right? That takes energy. You got to put energy in to break those bonds. You also have to overcome the intermolecular forces of the solvent, right? You have to pull the solvent molecules apart to make room for the solute. That's called making a hole. You make a hole for the solute. Then when you put the solute in, you get the intermolecular interactions between the solvent and the solute. That's the step 3. So 3 steps: break bonds, energy in. Break bonds, energy in. Form bonds, energy back. Remember, when physical or chemical reactions occur, the tendency is toward the lowest stable energy state. So when you get interactions, right, they draw each other together, they give up energy. So if you put energy in, that's endothermic. Right? Step 1, 2, 3. Delta H, delta H, delta H. This is going to be energy in. Right? Remember our sign convention? Energy in is positive. Energy in is positive. Energy back is negative. So when you form these bonds, you get energy back, exothermic. Now, why do some solutions feel hot, some solutions feel cold when they form? It's the balance. Right? If this together is greater than this one, we put more energy in, the solution is going to get cold. And that's what we do with cold packs in the hospital. Right? They got this calcium ammonium phosphate, I think it is, in this little packet in the bag of water, and you break it, mix it together, and it gets cold. Well, in that case, the heat of this third step is smaller. Absolute value is smaller than this value, so this one draws energy in more than it gives up. That makes it cold. If, on the other hand, you put this energy in and you get a whole lot back, a lot of energy back, then it'll be overall exothermic and get hot. So there's one of those packs in the hospital is hot pack too. I'm trying to think of what they put in it. They could do that. I can't remember what the compound is. But those are the 3 steps. Step 1, step 2, step 3, releases energy. This is the whole discussion about it. If you put them all together, the enthalpy of solution is a combination of these 3 steps. Okay, this is what it looks like on a graph. Overall, remember Hess's law? The enthalpy of a reaction. If you put 2 or more reactions together and you combine them into your target reaction, then you can add up the enthalpies and find out what the overall enthalpy is. That's Hess's law. Well, it works for this too. If this reaction, you put in energy here and you get a whole lot back, then the difference between them here is exothermic. Right? More negative is exothermic. But in this one, it's endothermic because you put in a lot of energy and you only get a little bit back. So that's a positive delta H. It's endothermic. So why do some solutes not mix with other solvents? Now we're talking about intermolecular forces again.
Why do water and oil, they don't mix, right? How does delta H play a role in that? Well, let's see. Water is polar, right? Hydrogen bonding material. Oil is nonpolar. It has, the only option it has is London dispersion forces. Well, let's see what we have here. Polar solvent, nonpolar solvent. Here we go. There's oil and there's water. So delta H going in is the solute. It doesn't take much energy, right, to break those London dispersion forces for the oil. It takes a lot of energy to break the bonds for the polar solvent, water. Delta 3, what do you get back? You get practically nothing back, right? Because water and oil, they don't have the same attraction. Right? Oil is what's known as hydrophobic. So what's the delta H of solution? It takes a very large input of energy that you get nothing back from. So delta H is very endothermic, and it's difficult to do that, right? You can do that, right? When you steam clean an engine, you ever seen that done? This guy with big insulating gloves and protective clothing and everything gets out the steam tube with a big wand on it, and high pressure steam comes out the end. You don't want to get near that, it'll burn the crap out of you. And you just clean the engine off. Well, it's not just by the force of the steam striking that engine. It's not just the heat that melts it. The grease on your engine actually dissolves in the water because you put a lot of energy into it, right? So oil at room temperature doesn't dissolve in water because there's not enough energy, right, to make it happen. But if you get the energy high enough, you can make it happen. Okay? And the same thing happens for nonpolar solvent and polar solute. You still need a large amount of overall energy to make it happen. Whereas if they're both nonpolar or they're both polar, then you get a small amount of solution energy required and the process goes easily. Okay, so we have this rule of thumb. You may have heard it before. Like dissolves like. Nonpolars dissolve in nonpolars, and polars dissolve in polars. That's a rule of thumb, right? But there are various gradations in between. You can still get a very dilute solution formed from some nonpolars and polar solvents. Right? And that's another case of nature doing what it does and we try to wrap our heads around it. Right? It's on a continuum, actually. So when we talk about it this way, we're saying hard and fast. Right? These two don't mix and these two don't mix. Well, yes and no. Okay. It depends on the particulars. Okay. Let me see, where am I going with this one? Oh, this is just a summary. All right, we probably already covered this. There's like dissolved like. Remember we talked, when in the first semester we talked about I just remembered what I was trying to think of weeks ago, valence bond theory, as opposed to molecular orbital. Okay, back to the topic. When we talk about molecular orbital theories, we invoke probabilities. When we talk about the distribution of electrons around atoms, we talk about probabilities. Most probable to find the electron in this particular space. Probabilities are unavoidable because we don't know the particulars enough in how atoms behave that we can say definitively this is going to happen or that's going to happen. So we have to speak in probabilities. So what's the probability of the mixed state of a solute in a solid? If the probability is high, it will happen. If the probability is low, it won't happen. And that links into the amount of energy required to make it happen. If the amount of energy is very high, probability is low. If the amount of energy is low, probability is high that you'll get a solution. These processes that require large amounts of energy tend not to occur. Doesn't mean they don't occur, they just tend not to. Okay. So, what are some factors that affect solubility? That is, whether or not something will form a solution or how much of the solute will go into solution. Because you can reach a limit. Right? You can only form so many holes in your solvent for the solute to go into. And when they run out, that's it. No more goes in. That's solubility. So structural effects, polarity, we've talked about those already. We can also talk about pressure effects. Those are involved with dissolving a gas into a liquid or a solid. So the higher the pressure, you can get more gas dissolved in the solvent. Temperature effects. And we generally focus on the aqueous solutions because most of my students come through here in the life sciences anyway. So we want to stay true to the biochemistry of living systems is water-based. Structural effects, okay. So remember I mentioned hydrophobic, there's also hydrophilic. In other words, water loving. That's what philios is the Greek word for, it's one of the Greek words for love. So water loving. And those are polar substances, simply because water is a polar compound. Hydrophobic are non-polar substances. They're water fearing. Phobos means to fear. Pressure effects. Right? This is Henry's law. So the concentration of your gas dissolved in solution is proportional to the pressure of the gas over the solution. So if you have a container with a solution here and it's sealed, there's a gas here, this is the solute, and this is the solvent, liquid. Then the pressure here determines the concentration there. If you increase the pressure, you increase the concentration. Okay, and this is a proportionality constant, which varies from one gas to another. Right? So if you have a solution down here, you have a gas overhead, and all you have to do, remember Boyle's law, pressure volume? If you decrease the volume, you increase the pressure. So here we're squeezing it. We increase the pressure, and more of it goes into solution before it reaches an equilibrium state. Right? Remember where vaporization matches condensation. Well, actually, this is not condensation, excuse me. This is dissolution. How about temperature effects? Most of the time, when you increase the temperature, you get more solid dissolved in the liquid solvent, in water in this case. Most of the time. There are exceptions where increasing the temperature decreases solubility, but they're rare. And predicting this dependence on temperature is very difficult, probably because we really don't understand. We don't have a viable theory that works for this process. Now, the solubility of a gas decreases as we increase the temperature. Right? That's why I take my pop and I put it in the refrigerator before I even open it. I don't open a bottle until it's cold, because lower temperature means more gas dissolved in the pop. So when you open it, try that. Put a 2-liter bottle in your refrigerator and leave it there for a day, and then leave one out on the counter. The same, right, we want to keep everything the same, so the same manufacturer, the same whatever. Pull them out, and then pop the cold one, and you hear a fizz or sound. You pop the hot one. It's louder, isn't it? Right? Because there's more gas pressure in there for a higher temperature. That's typical of gases. And here's solubility, right? And it varies, right? It's difficult to predict. Let's see, solubility of solids, excuse me, we're not talking about gases now. Solids dissolve. So hotter you get, the more sugar goes into solution, the more potassium nitrate goes into the solution, more sodium nitrate, sodium bromide, potassium chloride, sulfates. Sodium sulfate decreases solubility with decreasing temperature. And cesium sulfate. So something about the sulfur, I think, that makes them less soluble with higher temperature. Solubility of the gases, okay, so increase the temperature, decrease the solubility of methane, oxygen, carbon monoxide, nitrogen, and helium. Helium is almost flat, and it's very low solubility to begin with. So when we used to run an instrument where we had very, very high pressures, 100 atmospheres pressures in this chromatograph, we would run our solutions through the tube, and when it comes out the other end, pressure was released. Right? There'd be pressure on this side, no pressure on this side. So if there is any gas dissolved in that solution, it would come out of solution instantly at your detector, and that would be murder for your detector. So our solution had to be, all gases had to be removed. Right? And the way we did it was we would sparge it with, in other words, bubble helium through it. Helium would displace all these other gases. And helium itself is very insoluble, so it wouldn't cause a problem. Now they use vacuum extraction. They put your solution goes through a vacuum system as it enters the machine, and that extracts all the gases. Okay, so here we have an example of vapor pressure in solutions. So what happens is we have these two containers, and our solute is low concentration here and high concentration here. But the solvent is non-volatile, like water. It's relatively non-volatile. But the solute is a volatile compound. So it has a vapor pressure in the head. So it produces a vapor pressure here and a vapor pressure here. Okay. High concentration on this side means that the vapor pressure of that dissolved gas actually, it's the other way around. This example says the solvent is volatile, and the solute is not volatile. Okay, say that again. The solvent is non-volatile, like sodium chloride, sugar, but the water has a volatility. It's low, but it's there. So the pressure here would be greater than the pressure there, because the concentration of solute interferes with the movement of solvent into the vapor phase. Right? It has simple physical blocking of the surface by the presence of these molecules and atoms and ions, and because they attract water.
and then keep it from moving into the vapor phase. In this example, we've got pure water over here and a high concentration of something over here. Could be salt, could be sugar. The one I like best is sulfuric acid. It works the best. And you have these two containers here, and over time, this vapor pressure up here is higher than it is over here. So the vapor pressure formed by this pure water is higher on this side, and which consequently forces more of the water into this solution on the other side. And eventually, all the water's gone here and it's over there. Okay, so how do we determine the vapor pressure of the solution as compared to the vapor pressure of the pure solvent? Okay, again, the solvent is volatile and the solute is not. So if we know the mole fraction of solvent and we know its pure vapor pressure, then all we have to do is multiply this fractional number times the pure vapor pressure and we get the solution vapor pressure. Okay, so if the mole fraction of the solvent is, say, 0.2 mole fraction, then what would be the mole fraction of the solvent? Oh, excuse me, solute. There, solute. What would be the mole fraction of the solvent if these were the only two components? It would be 0.8, right? So if you know the mole fraction of the solute, then you can calculate the solvent mole fraction and use it in this formula. Okay, what does this mean? Oh, well, that was, doesn't identify here. That was Raoult's law. This guy right here, Raoult. He's the one that said that right there. Oh, there it is. Can't read on screen. Raoult's law. So as the mole fraction of the solvent increases, the solution vapor pressure, let's see, the mole fraction of the solvent increases, right, the vapor pressure increases until you get to pure solvent, and then that's the highest it can get. Can't go any higher. But as you add more solute, you decrease the mole fraction of the solvent, and you'd also decrease its vapor pressure. Now that's for the solute that's not volatile. What if you put a volatile solvent in solute in your solvent, like alcohol, ethanol in water? What do you do then? Well, then you have to modify your formula. So the total pressure is due to the contribution from one component plus the contribution from the other. Right? So if you've got a volatile solvent and a volatile solute, then you have to do a calculation for each one and add them together to find out the total. Now, if it's an ideal solution, this value would be the same whether this was volatile or not. Doesn't matter. And any solutions that are not ideal, they approach ideal as you get closer to one side or the other. Mole fraction of zeros or one. So what does that look like graphically? This is the partial pressure of A, right? As the fraction of A increases, its partial pressure increases. Remember Dalton's law of partial pressures? The pressure of a gas is the summation of the partial pressures of each of the components. Okay. So the partial pressure of A is this, increasing, and as it increases, the partial pressure of B decreases. So when you add them together, so this one plus that one is this line right here between these two. That's an ideal solution. It follows that straight line connector between pure B and pure A. If there's a deviation, it could be either a convex or a concave deviation. So in this case, when you mix them together, the mole fraction favors an increase in each one. In this one, it favors a decrease in each one as you add the other one. Right? So what's happening in there? In this one, you have very, very weak solute-solvent interaction. In fact, they might even be repulsive. In this one, you have strong solute-solvent interaction, which depresses their vapor pressures, right? It keeps them in solution, doesn't let them go. All right, so let's see if we can find some examples of that. All right, here's our ideal solution. Benzene and toluene, they're perfect for each other. They produce an ideal solution. Whereas the deviation is negative here for acetone and water. In other words, you get that concave because acetone and water are very strongly attracted to one another. Whereas if you mix ethanol and hexane, they will dissolve in one another to a certain extent, but there's not a strong interaction. Notice that ethanol has hydrogen bonding available, and hexane doesn't. Right? So they virtually don't like each other very much. They'll coexist up to a point. And the delta H for this solution is endothermic. In other words, you put energy back in and you don't get much back. That's one of those graded concepts, right? It's not just like dissolves like, but there's gray area in between. And these types fit in the gray area. Whereas this exothermic, where you get acetone and water, you can get exothermic reactions for a lot of different things. That's why they say, do as you oughta, add acid to water. You add acid to water, not water to acid, because when you form the solution between water and strong acid, this works for strong base too. It's extremely exothermic. It's got so much heat in it, it could boil the water. If you add acid to water, then there's so little water there, it could boil it and spatter in your face. So you have lots of water and you add acid to that, so that the large amount of water will dissipate the exothermic energy of solution. Okay. So which one of these would be ideal, which would be positive, which was negative? Let's look for the ideal. Let's see. Hexane is nonpolar, chloroform is nonpolar. Wait a minute, here we go. These are nonpolar. I bet this one would be ideal. Ethanol and water are strongly attracted, so they would be a negative deviation. This would be a positive deviation. Let's see if I'm right. Oh, well, I thought I had animation for it. So I guess you'll have to take my word for it. Or see if the book agrees with me. All right, colligative properties. What is a colligative property? Colligative is a word that means the property does not depend upon the identity of the solute. In other words, if you dissolve a mole of sodium chloride, let's use something else, because sodium chloride dissociates into individual ions, and that's deviation. How about we dissolve a mole of sugar table sugar and a mole of glucose. They're different. Table sugar is a disaccharide, glucose is a monosaccharide. So it doesn't matter. A mole of one, mole of the other, you still get the same response. Boiling point elevation, freezing point depression, osmotic pressure. So the solute doesn't matter. That's a colligative property. We're going to use that colligative property for freezing point depression. So let's look at these individually. What do they mean? Boiling point elevation means that the boiling point of the solution is higher than the pure solvent. So when you add solute to it, you cause the boiling point to go up. Boiling point elevation. That's why when you mix ethylene glycol in your radiator, the boiling point of the solution in your cooling solution in your engine is higher than 100 degrees. A lot higher. So you can run that fluid at a higher temperature to cool your engine without boiling away. And this is the formula that you use. So the change in temperature is the important one. The change in temperature from the boiling point, elevation, right? So if the boiling point is 100 degrees for water and you add something to it that makes the boiling point 110 degrees, the change is 10 degrees. That's what delta T means. M is the molality of the solute, right? Moles per kilogram of solvent. And then the Kb is specific for the solvent. So it doesn't matter what the solute is that you put into solution, but it does matter apologies. I must have run past. There we go. For the solvent, though, it does matter. And this particular constant is specific for the solvent. So it'll be different for water, it'll be different for, let's say we use lauric acid as our solvent in our experiment. And the solute is benzoic acid. So this is the molal boiling point elevation constant. So let's look at that for just a second. Delta T equals K sub B and M of the solute. Okay. Look at the units of measure. What are the units of measure here? Degrees centigrade, Celsius. Okay. What are the units here? Well, they're molal. But what is molal? It's moles per kilogram. Moles of solute per kilogram of solvent. All right. So what does Kb have to be? Oh, excuse me. Yeah, Kb has to be degrees C kilograms per mole. Okay. In order for you to leave this degrees Celsius here, you got to cancel the kilograms, cancel the mole. So the units of measure for this will be degrees C kilograms per mole. Or sometimes they say degrees C per molal. But for our purposes, this is better because we're looking for how many moles of solute are dissolved in the solvent. So that's more important. This is a better use. Well, we're not going to use this one. We're going to use its sister here, freezing point depression. So this one, what's the freezing point depression? Well, when you dissolve your solute in the solvent, the freezing point might be 0 degrees Celsius for water, but if you dissolve something into it, you could decrease the freezing point to minus 10 degrees Celsius or minus 20 degrees. Right? Think ice cream freezer. Throw salt on your ice, decreases the temperature. Right? You can freeze your ice cream or custard, whatever the case may be. but the same units measured are here. And this is actually absolute. What is the temperature change? If it's freezing point depression, in that case, it would be 10 degrees or 20 degrees. Okay, you just throw the sign out. All we care about is the difference. Okay. And I'm getting short on time. I'm gonna have to skip this. This is a theoretical discussion of this is a phase diagram, I think. So we're showing the difference here in boiling point or the difference here in freezing point. Yeah, there's the triple point right there. So you shift, this is the pure vapor pressure of pure water, and you shift the diagram down to here. You move the triple point down to here. You also move the phase line for each one there and there. All right. I think I am, as usual, running out of time. Yeah, I'm going to have to skip over this problem. There's a correction factor. If your solute dissociates when it goes into solution, like salt. When salt goes into water, you put 1 mole of sodium chloride in water, what do you get in ions? You get roughly 2 molar ions. Right? And that's what matters. It's the molality of the actual solute particles. Right? So we have a correction factor, the Van Hoff correction factor. And generally speaking, you look for whether the solute will dissociate when it goes into solution. That's ionic in most cases. So you can throw, well, yeah, for our purposes, ionic. So sodium chloride would have a Van Hoff, right, of 2. Calcium chloride would have Van Hoff of 3. Right? And let's see, aluminum chloride would have a Van Hoff of 4. So this makes 2, this makes 2 plus 1 is 3, and 3 plus 1 is 4, is the correction factor. Well, where does that correction factor go? Goes right here. So if you say the molality of the solute before you put it in, then you have to multiply it by that factor right in here. So it'd be Ki little m. All right. Now that's the ideal situation. But the actual calculation of the Van Hoff factor has to take into effect this little number right here, ion pairing. In solution, sometimes you get the ions repairing up. And now instead of 2, you've got 1 again. So for this one, the actual value is less than 2, like 1.8. And you only know that if you look it up in a reference manual. Right, but theoretically, this is what you would get. Right? Potassium nitrate dissociates into potassium nitrate ions. Sodium phosphate has 3 sodiums in 1 phosphate ion, makes 4. It's most important for very highly charged ions. Right, small ions with a large charge on them, like calcium with a 2+ charge, probably you'd see significant ion pairing in this one, but less so in this one. Oops. So there's your modified equation. You stick I in there. Okay. Let's see. Boiling point on phase depression. This is a sample problem. Okay, we're determining the molality of the solution. Next slide. Oops, wrong way. And continuing on. So this is that K value. I think that's for water. This is the change in temperature, and this value is 0.2290. So this is the molality, and this is the Van Hoff factor that's incorporated. All right, there's lots of math here, and I'm sorry we don't have time to go into it. But eventually, you can use it to, in this case, to calculate what mass percent of each one there was. Sodium chloride and sucrose. Mass percent composition. In this case, we had both sucrose and both sodium chloride in that solution. So that's a complex mixture. We'll cover stuff like this in our review session. Take it in more detail. Okay, let's see. Okay, plant cells normally have a molality of 0.25 in their cytoplasm. So if you immerse this in aqueous solution with a freezing point of minus 0.246, will the cell explode, shrivel, or do nothing? So the key there is the solution the same molality as the cell, right? Because if it is, it's isotonic and nothing will happen. But if the solution is hypertonic, it will move water out of the cell in the solution and shrivel. But if it's hypotonic, water will move through the cell membrane into the cell and explode. So we have to do the calculations and find out, you know, what is the molality of the solution? The solution is less molar than the solid, than that one. There we go. Water will move into the cell, and the cell will explode. Our last colligative property, osmotic pressure. What's osmotic pressure? Actually, I probably should have done those first two slides, but previous two slides after this discussion. Because now we're going to talk about osmotic pressure, and that's what causes the cell to explode. So the formula is similar, right? The osmotic pressure here in atmospheres is molarity, not molality, but molarity, times the gas constant, and this is the one 0.08206 liter atmospheres per mole K. And this is temperature in Kelvin. And you can calculate the atmospheric pressure, osmotic pressure, based on the solution concentration. So here's how we determine, this is one way to determine osmotic pressure. There's your membrane. There are two types of membranes. There's the semi-permeable, and there's the selectively permeable. Okay? There's a very fine difference between the two. Semi-permeable, only water passes, or small gas molecules. Selectively permeable can be engineered to pass different size molecules. So it can be set up so that it will pass a certain size, say, organic molecule, and not other ones, or it can be designed, the membrane can be designed to pass non-polar components and retain on one side of the membrane, ionized components. So semi-permeable membranes are the types that you find in dialysis machines. If you know anybody that's undergoing kidney failure, then they have to undergo dialysis and they use selectively permeable membranes. That allows poisons to pass through the membrane and be expelled from the body and allows your body to retain the good stuff. But osmotic pressure, if we have a solution in here and pure solvent in here, and then we submerge it, the solvent would be water. This solvent is water, and this is an aqueous solution. Then which way is the water going to move? Well, since only water passes through a semi-permeable membrane, it's going to move to the solution that's higher concentration in the solute. So it's going to move through the membrane here and try to dilute that solute. Right? Because water moves both directions in that membrane. Water can move this way and move that way. But with the solute in there, it interferes with the movement of water through the membrane. It simply gets in the way. So water is going to move predominantly in here into this container. And notice that as it does, this level rises. And it rises to a point where it reaches equilibrium, where the water is moving equal rates back and forth. And at that point, the difference in the height from here to here is the osmotic pressure. You can measure that depending on whether, if you know the characteristics of that solution, you can calculate what the pressure is in atmospheres. This is another way to look at it. You just have a U-tube with a membrane here, and you notice that the water is moving this way. It decreases this side, increases that size, and there's the osmotic pressure. And there's your formula again, oops, with the Van Hoff correction. So you have to consider that Van Hoff correction for any of these colligative properties. Okay. Here's another problem that we will have to forego the pleasure of diving into it. It's just to make note that this osmotic pressure is the difference between full atmosphere and the actual pressure. Actually, not the difference, the ratio. And then we want to solve for molarity. Right? There's your gas constant. There's your conversion to K for the temperature. You have to know the temperature to do the calculation. And this osmotic pressure thing is used to determine the molar mass of the solute. We're going to use freezing point depression to determine the molar mass of benzoic acid and compare that to the given value. But when we do that, what do you need to calculate the molar mass, or molecular weight? That's the way I learned in school. Molar mass is equal to mass per unit mole. So you need to know how much of the substance and how many moles does that represent. Okay. So we're going to know the mass of our benzoic acid. We need to know how many moles that is. So we use the freezing point depression procedure and that formula to determine the number of moles of benzoic acid. And once we do that, we can do the calculation. All right, I think I'm almost down to the end. Colloids. Yeah, okay, this is the last discussion, colloids. What is a colloid? Well, remember, we talked about homogeneous and heterogeneous mixtures. A colloid is a mixture, but it's not a solution. It's based upon
the size of the solute particles. If the solute particles are small enough, they can be indefinitely suspended in the mixture, and they can mimic a solution. So it's actually a suspension of tiny particles in some medium. Now, how do you know it's a solution or a colloid when it looks like a solution? Well, we use what's called the Tyndall effect. So if you have a solution here in this clear beaker, there's your solution. If you shine a flashlight, right, shine a beam here, then if it's a solution, it'll come out the other side and you can see it on this side. But you cannot see it in the solution. In other words, there's no refraction. There's no bouncing off the particles. If it's a colloid, you will see the beam of light in the solution, or in the, not solution, in the colloid. Now, what kind of colloids are there? Right? You like Jello? Yellow is good for filling you up and giving you no nutrition whatsoever. That's because Jello is a colloid mixture of a protein in water, but that protein is non-nutritional. As you break it down, the amino acids that come out of that protein, your body can't use them. You just flush them out. So these are different types of colloids. Right? The one I was just talking about was, let's see, that protein is a solid in a liquid. That's a gelatin. That's Jello. A liquid dispersed in a gas is a fog or an aerosol. Let's see, a solid in a gas is a smoke. It could even be living, it could be bacteria. A gas in a liquid, whipped cream, so that's a foam. Shaving cream. Liquid in a liquid is an emulsion. So when you milk, homogenized milk is an emulsion. You know how they make homogenized milk? On the industrial scale. If you take raw milk, just let it sit, the fat will separate. You get the cream on top. But if you take that milk and you send it through your clean stainless steel pipes and through a grating with very, very tiny holes under high pressure, it just drives it through that thing. It breaks those fat globules up into very small particles. And they stay suspended. You don't get separation. Oh, so you know about that. Did you turn the teat up and?
Set the farmer up, break it down, take the little film out that we put around this, there's a spring, and we put a film and it would catch little tiny things. It's so gross, it felt like pieces of cheese when you took it out and straight off, but they were just so tiny. So.
Uh-huh.
But yeah.
Let's see. You can make a solid foam, right? Gas in a solid. I've seen the pictures or videos of these bricks, these little ceramic bricks, and they weigh nothing. They're just ounces. But you take a blowtorch on one side and feel or measure the temperature on the other side, there's nothing there. No temperature change at all. They're almost perfect insulators because of all that trapped gas in the solid. It was that type of technology that was used on the space shuttle tiles on the bottom to protect the bottom from overheating during re-entry. Let's see, ruby is a solid in a solid. colloid type. So, how can you destroy a colloid? Well, there are several ways. What you need to do is coagulate it. In other words, you need to make those particles stick together so that they're too heavy and they drop out of solution. And that's what you do when you churn butter.
When you test for mastitis in cows.
Uh-huh.
It coagulates like Jello milk does.
Oh,
So it's got a little dye in it too, and if you turn it over and flops like Jello, it's not running anymore, you get a mastitis.
uh-huh. And then what's that, bag balm? And you slap the bag balm on them? I use it on my feet. I think they've got some more advanced stuff now.
Udder butter.
Udder butter.
Soothe them.
Okay.
Soothe the heat and pain.
Yeah.
And then you gotta milk them out completely, chunks and all.
Oh, that sounds like fun. By hand?
Yeah.
Use a machine?
We set them up on a machine, but it's disconnected, so theirs goes straight to a bucket. It
Uh-huh.
doesn't go through the pipes.
Okay.
It just goes through the tube.
Now Greenbrier?
I worked this is when I was at WVU, I worked on the dairy farm.
Okay. Oh, it belonged to WVU? Okay.
I worked on the animal science farm.
Okay. We had one of those at LSU, and they had this dairy outlet. You go in and buy stuff that the students make, and ice cream, the best ice cream in the world. Okay, so you need to coagulate. So if you have a colloid with proteins in it, usually the best way to do it is to heat them, and it would destroy the structure of the protein and make it coagulate. Or you could change the ionic strength. You could salt it out or use acid, and that will cause it to drop out of solution.